Physics once made a prediction so catastrophically wrong that it broke the entire discipline. Not by a little, not by a factor of 2 or 10 or even a million. By 10 to the power of 120. That is a 1 followed by 120 zeros. It is a number so large that if you tried to write it out, digit by digit, you would run out of atoms in the observable universe before you finished. And this wasn't some fringe theory cooked up in a basement. This was quantum field theory, the most successful framework in the history of science, the same set of equations that predicted the electron's magnetic moment to 11 decimal places, the same machinery that gave us transistors and lasers and every piece of technology that makes modern life possible. It tried to calculate the energy of empty space, the energy of nothing, the energy sitting in the vacuum between atoms, between galaxies, between your eyes and this screen. And it got an answer so violently wrong that physicists have spent half a century trying to explain how they could have failed this badly. They call it the vacuum catastrophe. Some call it the cosmological constant problem. A few just call it embarrassing. Because here's the thing. Energy isn't a thing. It isn't made of particles. It isn't a substance you can bottle or weigh or point to. And yet, quantum mechanics insists that the vacuum, the so-called emptiness of space, is seething with it. Particles flickering in and out of existence. Fields humming at their lowest possible state. A background hum of reality that should, by every calculation we know how to make, have torn the universe apart 13 billion years ago. But it didn't. We're still here, and no one can tell you why. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. Energy is something everyone knows about, and nobody can explain. Ask a physicist to define it, and watch them squirm. They'll talk about joules and watts and conservation laws. They'll mention kinetic energy, potential energy, thermal energy, chemical energy. They'll draw diagrams with arrows and springs and falling objects. And if you press them hard enough, if you keep asking what energy actually is at the most fundamental level, eventually they'll admit something uncomfortable. They don't know, not really. Not in the way you can point to an electron and say that's a particle, or point to a wave and say that's a disturbance moving through a medium. Energy is slipperier than that. It's a concept, a property, a number that stays constant when you do the math right. But it is not a thing. That answer bothers people. It should, because we talk about energy like it's a substance. We say batteries store energy. We say the sun radiates energy. We say you need energy to get through the day. The language we use implies that energy is stuff, some kind of invisible fluid that flows from place to place, that can be bottled up and released, that moves through wires and muscles and chemical bonds like water through pipes. And in a practical, everyday sense, that mental picture works fine. It gets you through physics class. It helps engineers build power plants. It makes the world make sense, but it's wrong. The history of energy as an idea is a history of people slowly realizing they were chasing something that kept changing shape. The word itself comes from the Greek energia, meaning activity or operation. Aristotle used it to describe the actuality of a thing as opposed to its potential. A block of marble has the potential to become a statue. The statue is the energia, the realized form. That's poetic, but it's not physics. The modern concept didn't start taking shape until the 1800s, and even then it took decades of confusion and argument before anyone agreed on what they were talking about. In the early 19th century, the cutting edge of science was steam engines. Engineers in Britain and France were obsessed with extracting work from heat, and they needed a way to measure efficiency. How much coal do you burn? How much useful motion do you get out of it? The French physicist Sadi Carnot laid the groundwork in 1824 with a treatise on the motive power of fire. He didn't call it energy. He talked about caloric, an imaginary fluid that was supposed to flow from hot objects to cold ones. Caloric theory was wrong, completely wrong. But Carnot's mathematical framework for analyzing heat engines was so solid that it survived the collapse of the theory it was built on. Then came James Joule, a British brewer and amateur scientist who spent years obsessively measuring the relationship between heat and mechanical work. He built paddle wheels that churned water inside insulated containers. He measured how much the water warmed up when the paddles turned. He calculated how much mechanical work it took to produce a given amount of heat. And in 1843, he announced that heat and work were interchangeable. You could convert one into the other at a fixed rate. A certain amount of mechanical work always produced the same amount of heat, every time, no exceptions. That was the crack in the wall. If heat and work were two forms of the same thing, then maybe that thing, whatever it was, could take other forms too. Maybe it was conserved. Maybe the total amount of it in the universe never changed, just shifted around from one shape to another, like water changing from ice to liquid to vapor, but never disappearing. The German physicist Hermann von Helmholtz formalized this idea in 1847 in a paper titled On the Conservation of Force. The word he used was Kraft, which translates awkwardly as force, but really meant something closer to what we now call energy. Helmholtz argued that the total Kraft in an isolated system, mechanical, thermal, chemical, electrical, all of it remained constant. You could shuffle it around. You could turn motion into heat, or heat into light, or chemical reactions into electricity, but the sum never changed. It was the universe's way of balancing its books. By the 1850s, the idea had caught on. Scientists started calling it energy, borrowed from the Greek, and the principle of conservation of energy became one of the bedrock laws of physics. It worked. It explained steam engines and falling weights and chemical reactions and electric currents. It unified dozens of disconnected phenomena under a single framework. And yet nobody could say what energy actually was. They could measure it, they could track it, they could predict how much of it would show up in different forms after a collision or a chemical reaction. But defining it in a way that didn't just describe what it did, that was harder. The British physicist Lord Kelvin, one of the giants of thermodynamics, admitted the difficulty plainly. Energy, he said, is the capacity to do work, and work is the transfer of energy. If that sounds circular, that's because it is. You define energy in terms of work and work in terms of energy, and you end up chasing your tail. The definitions are operationally useful. They tell you how to calculate things, but they don't give you a picture of what the thing itself is. And the deeper you dig, the worse it gets. Take kinetic energy, the energy of motion. A car rolling down a hill has kinetic energy. You can calculate it easily, 1/2 the mass times the velocity squared. Simple, intuitive. Except, what does it mean to say the car has energy? The energy isn't sitting somewhere inside the car like gasoline in the tank. It's not a substance you could scoop out and put in a jar. The energy is a property of the car's motion relative to the ground. If you're standing on the side of the road, the car has a lot of kinetic energy. If you're driving alongside the car at the same speed, the car has zero kinetic energy relative to you. The energy depends on your reference frame. It's not an intrinsic feature of the car. It's a relationship between the car and the observer, and that makes it much stranger than a thing. Or take potential energy. Hold a ball above the ground and it has gravitational potential energy. Drop it and the potential energy converts to kinetic energy as it falls. That's the standard story. But where exactly is the potential energy while you're holding the ball? Is it in the ball? Is it in the earth? Is it in the gravitational field between them? The honest answer is that potential energy is a bookkeeping trick. It's a number you assign to a configuration of objects that tells you how much kinetic energy you'll get if you let the system evolve. It's not stored anywhere. It's a mathematical convenience that happens to predict the right outcomes. This is where people start to get uncomfortable. We want energy to be real in the way tables and chairs are real. We want to point to it. We want it to have a location and a substance. And physics keeps telling us no, it's not like that. Energy is more abstract. It's a property that systems have. It's a number that obeys certain rules. It's conserved, meaning the total doesn't change, but that conservation is less like protecting a pile of gold and more like balancing an equation. The universe keeps its accounts straight, and energy is one of the entries on the ledger. Thermodynamics made this even clearer. The first law of thermodynamics is just the conservation of energy dressed up in formal language. Energy can change forms. It can move from one system to another, but it can't be created or destroyed. The second law is darker. It says that in any real process, some of the energy will degrade into a form that's less useful. Heat spreads out. Concentrated energy dissipates. You can burn coal to boil water, to turn a turbine, to generate electricity, to charge a battery, to power a light bulb. And at every step along that chain, some of the energy leaks away as waste heat. The total energy is conserved, but the quality of it, the usefulness, declines. Entropy increases. The universe is running downhill, not because energy is disappearing, but because it's spreading out, becoming more evenly distributed, less capable of doing interesting things. And yet even that description, running downhill, makes it sound like energy is a thing flowing from high places to low places. It's not. Energy is a property of a system's configuration. A hot cup of coffee and a cold room have a certain total energy. Leave the coffee alone and the energy redistributes. The coffee cools, the room warms slightly, and eventually they reach the same temperature. The energy hasn't gone anywhere. It's still there, all of it, but now it's spread out more evenly. The system has moved from a low entropy state, where energy was concentrated in the coffee, to a high entropy state, where energy is distributed more uniformly. The second law says that process is irreversible. You'll never see the coffee spontaneously heat back up by sucking energy out of the air. Not because the energy isn't available, but because that configuration is overwhelmingly unlikely. This is the picture that emerged by the end of the 19th century. Energy is conserved. It can appear as motion, heat, light, chemical bonds, electrical currents, and more. All those forms are interconvertible, at least in principle, though the second law places limits on how efficiently you can convert them in practice. And underneath all of it, energy is not a substance, it's a property, a number, a way of keeping score. Then in 1905, Albert Einstein published a short paper titled, "Does the inertia of a body depend upon its energy content?" It was 3 pages long. It introduced an equation so famous it's been printed on t-shirts and coffee mugs and spray-painted on walls around the world. E equals mc squared. Energy equals mass times the speed of light squared. That equation changed everything. Before Einstein, mass and energy were separate. Mass was stuff, matter, the thing you could weigh on a scale. Energy was the ability to do work, a property that stuff could have, but not stuff itself. Einstein showed that the distinction was artificial. Mass is energy. Not mass has energy, or mass contains energy. Mass is a form of energy locked up in matter, enormous in quantity, because the speed of light is such a large number, and you square it. A single kilogram of matter, if you could convert it entirely into energy, would release about 90 quadrillion joules. That's roughly the energy output of a large nuclear power plant running for 2 years, all of it sitting quietly inside a kilogram of anything. A kilogram of water, a kilogram of rock, a kilogram of air. This wasn't just a curiosity, it was a redefinition of what matter is. Matter stopped being the solid, inert, fundamentally different stuff that occupied space. Matter became another entry on the energy ledger. You could turn mass into other forms of energy, which is what happens in nuclear reactions. You could, in principle, turn other forms of energy into mass, which is what happens in particle accelerators when high-energy collisions create new particles out of pure kinetic energy. The universe was more fluid than anyone had imagined. The categories we use to organize reality, matter versus energy, solid versus ephemeral, were dissolving. And if mass is energy, then the question of what energy is becomes even more urgent, because now you're not just asking about motion and heat and light, you're asking about the nature of matter itself. You're asking what the universe is made of at the most basic level. And the answer, as far as physics can tell, is fields, quantum fields, invisible, intangible mathematical structures that fill all of space. Particles are excitations in those fields, little ripples, little knots of concentrated energy. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. Matter and light and everything else are patterns of energy moving through fields that are always there, everywhere, even when nothing seems to be happening. Which brings us to the strangest part. Even when nothing is happening, the fields are still there. And quantum mechanics says they're not quiet, they fluctuate. Even in a perfect vacuum, even in a region of space with no particles, no light, no matter, the quantum fields are buzzing with activity. Virtual particles pop in and out of existence, borrowing energy from the vacuum for fractions of a second before disappearing. The vacuum itself has energy. Not a little, a lot. More energy than anyone expected, more energy than makes any sense. So much energy that if the calculations are taken at face value, the universe should have torn itself apart a fraction of a second after it began. It didn't, obviously. We're still here. The universe is nearly 14 billion years old and expanding at a measured, relatively calm pace, so something is wrong. Either the vacuum energy doesn't exist the way quantum field theory says it does, or it exists but doesn't gravitate the way general relativity says it should, or there's some other effect, some cancellation, some unknown piece of physics that makes the catastrophic prediction go away. We don't know which, we don't know why. What we do know is that the mismatch between theory and observation is not small. It's not a few percent. It's not even a factor of 10 or 100. The theoretical prediction for the energy of empty space is 10 to the power of 120 times larger than what we actually measure. That's a 1 followed by 120 zeros. The worst prediction in the history of physics, the largest discrepancy between theory and experiment ever recorded. And it's sitting right at the foundation of our understanding of what energy is. So when you ask a physicist to define energy and they hesitate, this is part of why. Energy is the thing that's conserved. Energy is the thing that takes many forms. Energy is a property of systems, not an independent substance. And also, Energy is the thing that should have destroyed the universe before it began, except it didn't, and we have no idea why. That tension, that unresolved crisis, is where the story really starts. Before 1905, the universe was simpler. Not actually simpler, but simpler in the way we talked about it. There were things, and there were properties of things. Matter was matter, energy was energy, mass was a measure of how much stuff you had. Energy was a measure of how much that stuff could move, or heat up, or change. The two were related, obviously. A moving object had energy, a hot object had energy. But mass and energy were fundamentally different categories. You could convert energy from one form to another, kinetic to thermal, chemical to electrical, but you couldn't turn mass into energy or energy into mass. That would be like turning a noun into a verb. The grammar didn't allow it. This wasn't just common sense. It was enshrined in the laws of physics as two separate conservation principles. The conservation of mass said that in any chemical reaction or physical process, the total mass stayed constant. Burn a log, and you get ash and smoke and heat. But if you collected every atom, weighed it carefully, the total mass would equal the mass of the original log plus the oxygen it consumed during burning. Nothing disappeared. Antoine Lavoisier had demonstrated this in the 1780s with careful measurements of chemical reactions in sealed containers. Mass in equals mass out, always, no exceptions. The conservation of energy said something similar. Energy couldn't be created or destroyed, only converted from one form to another. That principle had been hammered out over the course of the 1800s by Joule, Helmholtz, Kelvin, and others. Between them, these two laws formed a kind of double-entry bookkeeping for the physical universe. Matter had its own ledger, energy had its own ledger. Both books balanced independently, and there was no obvious reason to think they were connected beyond the fact that matter could have energy as a property. Then Einstein looked at the equations of electromagnetism, really looked at them, and noticed something strange. Maxwell's equations, the beautiful set of formulas that describe how electric and magnetic fields behave, predicted that light should travel at a constant speed. Not constant relative to some preferred reference frame or some invisible medium filling space. Constant relative to any observer, no matter how that observer was moving. That didn't make sense. If you're on a train moving forward and you throw a ball forward, the ball's speed relative to the ground is your speed plus the ball's speed. Basic addition. But Maxwell's equations said light didn't work that way. If you're on a train moving forward and you shine a flashlight forward, someone standing on the ground would measure the light moving at exactly the same speed you measure. Not faster, not slower, the same speed. Einstein took that seriously. He started with two assumptions. The laws of physics are the same in all inertial reference frames, meaning any frame moving at constant velocity. And the speed of light in a vacuum is the same for all observers, regardless of their motion. From those two principles, he rebuilt mechanics from the ground up. The result was special relativity, published in 1905 in a paper titled On the Electrodynamics of Moving Bodies. It was 26 pages long, and it dismantled 300 years of Newtonian certainty. Time was no longer absolute. Two observers moving relative to each other would measure time passing at different rates. Space was no longer absolute. Lengths contracted in the direction of motion. Simultaneity was relative. Events that appeared to happen at the same time in one reference frame could happen at different times in another. And buried in the mathematics of how energy and momentum transform between reference frames was a conclusion so strange that even Einstein seemed surprised by it. Mass and energy were not separate. They were different aspects of the same thing. He laid it out in a follow-up paper published later that same year, just 3 pages, with a title phrased as a question. Does the inertia of a body depend upon its energy content? The answer was yes. If a body emits energy in the form of radiation, its mass decreases. The relationship between the change in energy and the change in mass was direct, connected by a conversion factor equal to the speed of light squared. E equals mc squared. Energy equals mass times the speed of light squared. The equation is so famous now that it's lost its ability to shock. It's been printed on t-shirts worn by people who couldn't tell you what the letters stand for. It's become a symbol for genius, for science, for the mysterious power of mathematics to reveal hidden truths. But when you actually think about what it's saying, it's deeply unsettling. The speed of light is roughly 300 million meters per second. Square that, and you get 90 quadrillion, 90 with 15 zeros after it. So if you take 1 kilogram of mass, any mass, a kilogram of water or iron or air, and you multiply it by 90 quadrillion, you get the amount of energy locked inside that mass, 90 quadrillion joules. That's about 21 megatons of TNT equivalent. The atomic bomb dropped on Hiroshima released roughly 15 kilotons. A single kilogram of matter, fully converted to energy, would release more than 1,000 times that. And that kilogram could be anything. A bag of sugar, a textbook, a slightly overweight house cat. This is not energy the object has because it's moving or because it's hot. This is energy the object has just by existing, by being made of matter. Mass is energy in a dormant form, concentrated, stable, locked away. But it's there. The equation says so, and the equation, as it turned out, was right. Before Einstein, nobody had any reason to think this was true. Classical physics treated mass and energy as independently conserved. There was no hint in Newton's laws or Maxwell's equations or thermodynamics that you could turn one into the other. The conservation of mass had been tested over and over again in chemistry labs for more than a century. It worked. The conservation of energy had been tested just as rigorously. It worked too, but they worked separately. Combine them and you get something new. A single unified conservation law for mass energy. The total amount of mass energy in an isolated system is constant. Mass can decrease if energy increases. Energy can decrease if mass increases. The two quantities are interchangeable, linked by the speed of light squared. At everyday speeds and everyday energies, the effect is invisible. When you burn gasoline in a car engine, chemical energy converts to heat and motion. The mass of the exhaust and the energy released, if you add them up properly, do show a tiny decrease in total mass compared to the gasoline and oxygen you started with. But the decrease is so small, a few billionths of a percent, that no practical scale could measure it. For all chemical reactions, for all ordinary human-scale processes, the classical conservation laws are close enough. The errors are negligible. You can treat mass and energy as separate and you'll never notice the mistake. But at higher energies, the cracks appear. And once you know where to look, the evidence is everywhere. The first major hint came from the photoelectric effect, which Einstein also explained in 1905. It was a busy year. The photoelectric effect had been observed in the late 1800s when physicists noticed that shining ultraviolet light on certain metals caused them to emit electrons. That much was clear. What wasn't clear was why the effect depended on the color of the light and not just its brightness. Classical wave theory said light was a continuous wave of electromagnetic energy. If you shine a dim blue light on a metal, it should take a while for enough energy to accumulate to knock an electron loose. If you shine a bright red light with much more total energy, it should work faster. But experiments showed the opposite. Bright red light, no matter how intense, often did nothing. Dim blue light worked immediately. The effect depended on frequency, not intensity. High-frequency light, ultraviolet or blue, could eject electrons. Low-frequency light, red or infrared, couldn't, no matter how much of it you used. Einstein's explanation was radical. He proposed that light wasn't just a wave. It also behaved as if it were made of particles, discrete packets of energy he called quanta. Later, they'd be called photons. The energy of each quantum was proportional to the light's frequency. Higher frequency meant higher energy per quantum. Lower frequency meant lower energy. When a quantum of light hit an electron, it either had enough energy to knock the electron free, or it didn't. Adding more quanta didn't help if each individual quantum was too weak. It was like trying to break a window by throwing marshmallows at it. Throw 1,000,000 marshmallows and the window stays intact. Throw one rock and it shatters. Frequency determined the energy per photon. Intensity determined how many photons hit per second. Only the energy per photon mattered for ejecting electrons. This was the first solid evidence that light had particle-like properties. And if light, which everyone agreed was a wave, could also be a particle, then the line between waves and particles was blurrier than anyone thought. Later, in the 1920s, Louis de Broglie proposed that if waves could behave like particles, maybe particles could behave like waves. He was right. Experiments confirmed that electrons, protons, even whole atoms exhibited wave-like interference patterns under the right conditions: matter and light, particles and waves, mass and energy. The categories were collapsing. Einstein's equation was the key that unlocked all of it. If mass is energy, then particles, which have mass, are just concentrated packets of energy. And if energy can take the form of massless particles like photons, then the distinction between matter and radiation is not a wall, it's a spectrum. The most dramatic confirmation of E equals mc squared came from nuclear physics. In the 1930s, physicists started smashing atoms apart and measuring what came out. When a heavy nucleus like uranium splits into lighter fragments, a process called fission, the total mass of the fragments is slightly less than the mass of the original nucleus. The missing mass hasn't vanished. It's converted into energy, released as heat and radiation, and the kinetic energy of the flying fragments. The amount of energy released matches Einstein's equation exactly. Take the mass difference, multiply by the speed of light squared, and you get the energy output. A single uranium-235 nucleus weighs about 235 atomic mass units. When it fissions, the total mass of the fragments is about 0.2 atomic mass units lighter. 0.2 atomic mass units is roughly 3.3 times 10 to the negative 28 kilograms. Multiply that by 90 quadrillion, and you get about 30 million electron volts of energy per fission event. That's a tiny amount by everyday standards, but it's enormous by atomic standards. One fission releases millions of times more energy than burning a single molecule of gasoline. Scale that up to a kilogram of uranium, and you get the equivalent of thousands of tons of TNT. Scale it up to tens of kilograms in a bomb, or hundreds of kilograms in a reactor, and you get Hiroshima, Chernobyl, the entire nuclear age. The equation is not a metaphor. The mass genuinely disappears. If you could collect every particle produced in a fission reaction, weigh them with perfect precision, and compare that to the original uranium nucleus, the total would be lighter. The missing mass is gone. It's been converted into other forms of energy, exactly as Einstein predicted, and it works in reverse too. In particle accelerators, physicists collide particles at extremely high speeds. The kinetic energy of the collision can convert into mass, creating new particles that didn't exist before the collision. Smash two protons together hard enough, and you can produce a proton, an antiproton, and the original two protons, all flying apart from the collision point. The antiproton is new, it's made of energy. The kinetic energy of the original protons decreased, and a new particle with mass appeared. Energy became matter. This happens routinely. Particle accelerators are factories for turning energy into mass. They've created thousands of different particle species, some of which last for only fractions of a second before decaying back into lighter particles and radiation. But while they exist, they're real. They have mass, they have momentum, they interact with other particles, and they were born from pure kinetic energy following the same equation, E equals mc squared. This is the point where the question, what is energy, takes on a new shape. If mass is energy and energy is mass, then asking what energy is becomes the same as asking what matter is, and the answer, according to quantum field theory, is fields. The universe is filled with quantum fields, one for each type of particle. The electron field, the quark field, the photon field. These fields exist everywhere, at every point in space, all the time. A particle is not a tiny billiard ball bouncing through emptiness. A particle is a localized excitation in its corresponding field, a ripple, a wave packet, a knot of concentrated energy. When you say an electron has mass, what you're really saying is that the electron field, in the configuration corresponding to an electron, has a certain amount of energy density packed into a small region of space. That energy density is what we measure as mass. When the electron moves, the ripple moves through the field. When the electron interacts with a photon, two ripples in two different fields exchange energy and momentum according to the rules of quantum mechanics. The electron is not a thing that has energy. The electron is energy, structured energy. Energy that happens to be stable enough and localized enough that we can track it, name it, treat it as an object. Photons work the same way, but they're ripples in a different field, and the configuration of that field gives them zero rest mass. They still have energy, they still have momentum, but because they have no rest mass, they always move at the speed of light. They can never be at rest. If you tried to slow a photon down, it would cease to exist. Its energy would have to go somewhere else, into other particles, into heat, into some other form. You can't bottle light. You can absorb it, reflect it, redirect it, but you can't stop it and keep it. It's pure kinetic energy in field form. This is a completely different picture than the one Newton had or the one Lavoisier had. For them, the universe was made of objects, solid things with definite positions and velocities, moving through empty space according to deterministic laws. Energy was something those objects could have, a property that described their motion or temperature or configuration, but the objects themselves, the matter, was fundamental. Now we're saying the opposite. The fields are fundamental. The particles are patterns in the fields. And the thing we call matter is just one particular kind of pattern, one that happens to be stable and localizable, and that we've decided to call mass. Energy isn't a thing you add to matter. Energy is what matter is made of. Einstein didn't know all of this when he wrote E equals mc squared. Quantum field theory didn't exist yet. The electron had been discovered, but the structure of the atom was still mysterious. Protons and neutrons hadn't been identified. Quarks wouldn't be proposed for another 60 years. But Einstein's equation pointed the way. It said mass and energy are the same currency, just denominated in different units. And once physicists accepted that, the rest followed. If you can turn mass into energy and energy into mass, then mass is not a separate, inviolable substance. It's a form energy can take. A very stable, very dense form, but a form nonetheless. The philosophical implications are strange. If you hold a baseball in your hand, you're holding energy. Not energy the baseball has because you lifted it off the ground. Energy the baseball is. The atoms, the molecules, the protons and neutrons and electrons, all of it is energy arranged in a particular structure. If you could somehow annihilate the baseball completely, convert every particle into radiation, you'd release about 2.5 megatons of energy. You won't ever do that, because there's no natural process that can annihilate ordinary matter completely, but the energy is there. The equation says so. The baseball is frozen energy, solid energy, energy pretending to be a thing. And if that's true of a baseball, it's true of you. An average human body weighs about 70 kilograms. Multiply that by the speed of light squared, and you get about 6.3 times 10 to the 18th joules. That's 6 billion gigajoules. That's roughly the total energy consumption of the United States for 2 weeks. All of it sitting quietly inside the atoms of your body. You are, quite literally, an enormous reservoir of energy in a temporarily stable form, and you always have been. Every person you've ever met, every animal, every tree, every rock is the same. The universe is not made of matter and energy, it's made of energy that sometimes looks like matter. This realization sets up the next problem. If particles are excitations in quantum fields, and mass is just energy in a localized stable form, then what happens when there are no particles? What happens in the regions of space where the fields exist, but nothing is rippling through them? Empty space, a vacuum. Classical physics said nothing happens there. The fields are in their ground state, their lowest energy configuration, and the energy of that state is zero. But quantum mechanics says something very different. It says the fields are never truly still, they fluctuate. Even in a perfect vacuum, even in a region of space completely isolated from everything else, the quantum fields are buzzing with activity. Virtual particles pop in and out of existence, borrowing energy from the vacuum itself for fractions of a second before annihilating and paying the energy back. The vacuum isn't empty, it's seething, and if the vacuum has energy, then it has mass equivalence. Empty space weighs something. Not much per cubic meter, but space is big. Add it up across the entire universe, and the total is enormous, or it should be. Except when you calculate how much energy the vacuum should have, the answer you get is catastrophically, absurdly wrong. The prediction is 10 to the 120 times larger than what we actually observe. And that mismatch, that stunning failure of our best theories to predict something as basic as the energy of empty space, is where the story turns dark. The trouble with quantum mechanics is that it works perfectly, uncomfortably perfectly. It predicts experimental results to a precision so extreme that it borders on absurd. The magnetic moment of the electron, calculated using quantum electrodynamics, matches measurements to 12 decimal places. 12. That's like predicting the distance from New York to Los Angeles and being accurate to within the width of a human hair. No theory in the history of science has ever been tested so thoroughly or passed so convincingly. And yet, if you ask a physicist what quantum mechanics actually means, what it's telling us about the nature of reality, you'll get a different answer from every person in the room. Some will tell you particles don't have definite properties until you measure them. Others will insist everything that can happen does happen in parallel universes, splitting off at every quantum event. Still others will shrug and say the math works. Shut up and calculate. The theory is bulletproof. The interpretation is chaos. What nobody disputes is that quantum mechanics killed the classical picture of empty space. In Newton's universe, if you wanted to empty out a region completely, you could. Remove all the matter, remove all the light, remove all the heat, cool everything down to absolute zero, and you'd be left with nothing. Perfect vacuum, zero energy, a void. Quantum mechanics says no. You cannot empty space. You cannot reach zero energy. The universe has a minimum level of activity built into its foundation, and that minimum is not zero. Empty space, according to quantum field theory, is not empty, it's full. Not full of things you can see or touch or bottle up and sell, but full of fluctuations, of possibilities, of a kind of simmering potential energy that never quite settles down. The vacuum is restless. And that restlessness, it turns out, has measurable consequences. The man who made this unavoidable was Werner Heisenberg. In 1927, Heisenberg published what became known as the uncertainty principle, and it's been misunderstood ever since. Pop culture treats it like a statement about measurement, as if the problem is that looking at tiny things disturbs them. That's not wrong exactly, but it misses the deeper point. The uncertainty principle is not about our inability to measure things precisely. It's about nature itself refusing to have precise answers. The principle says you cannot simultaneously know both the position and momentum of a particle with perfect accuracy. The more precisely you pin down where a particle is, the less precisely you can know how fast it's moving, and vice versa. This is not a statement about clumsy instruments or insufficiently advanced technology. It's a statement about reality. The particle does not have a definite position and a definite momentum at the same time. Not because we can't measure both, but because both do not exist as definite values simultaneously. The universe at the quantum level is fundamentally fuzzy. Properties that classical physics treated as simultaneously well-defined, position and momentum, energy and time, are linked by an inverse relationship. Nail one down and the other spreads out. That's the rule, no exceptions. For energy and time, the relationship is particularly strange. The uncertainty principle says that if you measure the energy of a system over a very short time interval, the uncertainty in that energy measurement can be large. Extremely short timescales allow for extremely large energy fluctuations. Or to put it more provocatively, the universe allows energy to be borrowed as long as it's paid back quickly. The shorter the time, the bigger the loan. Borrow a little energy and you can keep it for a relatively long time. Borrow a huge amount and you have to give it back almost immediately. This isn't a metaphor, it's math, and the math has been tested. This is where virtual particles come in. If energy can fluctuate on short timescales, and if fields are everywhere, then even in a vacuum, even in a region with no real particles, the fields can briefly spike. A quantum field can borrow enough energy to create a particle and its antiparticle, a pair of opposite charges or spins, for a fraction of a second. Then the pair annihilates, the energy gets paid back, and the field returns to its ground state. These are called virtual particles because they don't stick around. They're not part of the permanent inventory of the universe. They exist in the gap between one moment and the next, in the space the uncertainty principle leaves open. You can't catch one, you can't bottle it, but they're there. And they have effects. This drives some physicists to distraction because calling them particles at all might be misleading. Richard Feynman, one of the architects of quantum electrodynamics, called them internal lines in a diagram, mathematical conveniences that help you calculate what happens when real particles interact. You draw a picture with squiggly lines representing photons and straight lines representing electrons, and some of those lines start and stop in the middle of the diagram without connecting to anything external. Those are the virtual particles. They show up in the math as intermediate steps. They contribute to the final answer, but they never appear as something you can directly detect, and yet the effects they produce are real, unambiguously, experimentally, repeatedly real. One of the cleanest demonstrations is the Casimir effect, first predicted by Dutch physicist Hendrik Casimir in 1948. Take two flat metal plates, place them extremely close together in a vacuum, a few micrometers apart, and the plates attract each other. Not because of gravity, not because of electrostatics, but because of the vacuum itself. Between the plates, only certain wavelengths of virtual photons can fit. Outside the plates, all wavelengths are allowed. The result is a difference in the vacuum energy density between the inside and the outside. That difference produces a measurable force pushing the plates together. The force is tiny, but it's there. Casimir measured it. Others have repeated the experiment. The vacuum is pushing. This is not a theoretical prediction awaiting confirmation. This is an observed phenomenon. The vacuum between two metal plates behaves differently than the vacuum outside those plates, and the difference produces a force. If the vacuum were truly empty, if it had zero energy and no fluctuations, the plates would feel nothing. They do feel something. That something comes from the zero-point energy of the quantum fields. Zero-point energy is the energy a quantum system has when it's in its lowest possible energy state. Classically, the lowest energy state of anything is zero. Stop all motion, cool everything to absolute zero, and you're done. Quantum mechanically, you can't stop all motion. The uncertainty principle won't let you. If you tried to pin a particle down to a single position with zero momentum, you'd violate the uncertainty relation. The system has to keep moving, just a little, even at absolute zero. That residual motion is the zero-point energy. Every quantum field has it. Every oscillator, every mode, every degree of freedom in the universe contributes a small baseline energy that can never be removed. For a single harmonic oscillator, the simplest quantum system you can write down, the zero-point energy, is half the quantum of energy associated with that oscillator's frequency. For a field, which is an infinite collection of oscillators at every point in space, you sum up the zero-point energies of every possible mode. And that sum, if you take it seriously, diverges. It goes to infinity. Or more precisely, it grows without bound as you include higher and higher frequency modes. That's a problem. Infinity is not a number you can measure. Infinity is not a number you can compare to experiment. So physicists impose a cutoff. They say, fine, we'll only include modes up to some maximum frequency, and above that we'll assume something else happens, new physics, a breakdown of quantum field theory, something that makes the sum stop growing. But even with a reasonable cutoff, say at the energy scale where we know quantum field theory works well, the contribution to the vacuum energy density is enormous. If you cut off the sum at the Planck scale, the energy scale where quantum gravity effects are expected to become important, you get a vacuum energy density of about 10 to the power of 113 joules per cubic meter. That's a 1 followed by 113 zeros. For comparison, the density of lead is about 11,000 kilograms per cubic meter, which translates to about 10 to the power of 20 joules per cubic meter, using E equals mc squared. The vacuum, according to this naive calculation, should have an energy density nearly 100 trillion times greater than solid lead. That vacuum would curve space-time so violently that the universe would have collapsed or exploded long before the first stars formed. It didn't. The universe is nearly 14 billion years old. Galaxies are spread across billions of light years. Space is expanding, but gently. The vacuum energy density we actually observe, inferred from measurements of the universe's expansion rate and the cosmological constant, is about 6 times 10 to the negative 10th joules per cubic meter. That's not 10 to the 113, that's 10 to the negative 10. The theoretical prediction and the observed value differ by a factor of 10 to the 123, or 10 to the 122, depending on whose calculation you trust and where exactly you set the cutoff. Either way, it's the largest mismatch between theory and observation in the history of physics, not the largest percentage error, the largest factor, the worst prediction ever made. This is the vacuum catastrophe, and it sits at the center of modern cosmology like a ticking bomb nobody knows how to defuse. Before we get to the catastrophe itself, we need to understand what the vacuum actually is in quantum field theory, because the vacuum state is not nothing. It's the ground state of all fields. Every field, electron, quark, photon, neutrino, all of them has a lowest energy configuration. In that configuration, there are no real particles, no excitations, no ripples propagating through space. But the fields are still there, still present at every point, still fluctuating within the bounds the uncertainty principle allows. The vacuum is the state where the fields exist but are not visibly doing anything, and even in that state, they contribute energy. Think of it like the surface of a pond on a perfectly calm day. No waves, no ripples, no boats, just flat water. Except at the molecular level, the water is never truly still. Individual molecules are jittering, colliding, exchanging energy. The surface looks smooth from a distance, but zoom in and it's chaos. The quantum vacuum is similar. From a distance, it looks empty. Zoom in to short enough timescales and small enough distances, and it's seething with activity. Particle pairs flicker into existence and annihilate. Field values spike and drop. The vacuum is a hissing static of quantum noise that never turns off. And this noise has structure. It's not random in the sense of being completely unpredictable. The fluctuations follow rules. They respect the uncertainty principle. They respect the laws of quantum field theory. And they have measurable effects on real particles moving through the vacuum. One of the earliest pieces of evidence came from the Lamb shift, discovered by Willis Lamb in 1947. Lamb was studying the spectrum of hydrogen, the simplest atom, one proton, one electron. According to the Dirac equation, which combined quantum mechanics with special relativity, certain energy levels in hydrogen should be exactly degenerate, meaning they should have precisely the same energy. Lamb measured them carefully and found they weren't degenerate. There was a tiny splitting, a small difference in energy between levels that should have been identical. The explanation, worked out by Hans Bethe and others, was that the electron in the hydrogen atom is constantly interacting with the vacuum fluctuations of the electromagnetic field. Virtual photons pop into existence, interact with the electron, and disappear. That interaction shifts the electron's energy very slightly, by an amount that depends on which orbital the electron occupies. The shift is tiny, less than 1 part in a million of the electron's total binding energy, but it's there, it's measurable, and it matches the predictions of quantum electrodynamics to extraordinary precision. The Lamb shift is not caused by any real photons. There's no external light shining on the atom. The shift comes from the electron interacting with the quantum vacuum, with nothing, except nothing is not empty. Nothing is full of virtual photons, And those virtual photons are real enough to change the energy levels of atoms. If the vacuum were truly empty, the Lamb shift would not exist. It does exist, therefore the vacuum is not empty. Another piece of evidence comes from the anomalous magnetic moment of the electron. The electron has a magnetic field like a tiny bar magnet. The strength of that field, measured in units called Bohr magnetons, should be exactly 2 according to the Dirac equation. It's not. It's about 2.002319. That extra 0.002 is the anomaly, and it comes from the electron interacting with its own electromagnetic field and with the virtual particles constantly appearing and disappearing around it. Calculating that anomaly requires summing up the contributions of countless virtual particle interactions, drawing Feynman diagrams with loops and squiggles representing photons and electrons popping in and out of the vacuum. The calculation is horrendously complicated, and the result agrees with experiment to 12 decimal places. You cannot get that kind of agreement by accident. The virtual particles contributing to the anomalous magnetic moment are doing something. They're not just mathematical fictions, they're part of the machinery of reality. So virtual particles are real in the sense that their effects are real. You can measure those effects. You can predict them with extraordinary precision. But they're not real in the sense that you can isolate one, study it, weigh it, or watch it decay. They live in the gaps. They exist because the uncertainty principle allows energy to fluctuate briefly, and those fluctuations mean the vacuum has energy, not zero energy. Some non-zero baseline energy density filling every cubic meter of space in the universe. For most of the 20th century, physicists didn't worry too much about that baseline energy. You could subtract it off. You could say, fine, the vacuum has some constant energy density, we'll call that zero, and measure everything relative to it. Absolute energy doesn't matter in most physics problems. Only energy differences matter. If every point in space has the same vacuum energy, it doesn't affect how particles move or interact or decay. It's just a background, a constant offset you can ignore. That approach worked for decades. Particle physics went on without it. Quantum electrodynamics, quantum chromodynamics, the standard model of particle physics, all of them were built and tested without anyone needing to care about the actual value of the vacuum energy density. Then cosmology entered the picture, and in cosmology, absolute energy does matter. Because, according to general relativity, energy curves space-time, all energy, including the energy of empty space. If the vacuum has a non-zero energy density, that energy gravitates. It affects the expansion rate of the universe. It determines the curvature of space-time on the largest scales. You can't ignore it. You can't subtract it off. The vacuum energy density shows up directly in Einstein's equations as the cosmological constant, and its value determines the fate of the universe. Is space flat, open, or closed? Is the expansion accelerating or decelerating? Will the universe expand forever or eventually collapse? All of that depends on the energy density of the vacuum. In the late 1990s, observations of distant supernovae revealed that the expansion of the universe is accelerating. Galaxies are not just moving apart, they're moving apart faster and faster. Something is pushing space outward, and that something looks an awful lot like vacuum energy, a non-zero cosmological constant, dark energy. The terms are not quite synonyms, but they point to the same phenomenon. The vacuum has energy. That energy has a repulsive gravitational effect. And that repulsion is causing space itself to expand at an accelerating rate. The measured value of the cosmological constant, extracted from supernova data and cosmic microwave background observations and large-scale structure surveys, corresponds to an energy density of about 6 times 10 to the negative 10th joules per cubic meter, or in mass units, about 6 times 10 to the negative 27th kilograms per cubic meter. That's almost nothing. A teaspoon of vacuum weighs less than a billionth of a billionth of a billionth of a gram. But space is big, really big. Sum that tiny density over the entire observable universe, and you get a total dark energy content that outweighs all the stars, all the galaxies, all the visible matter by more than 2 to 1. The vacuum is the largest contributor to the energy budget of the cosmos. And that measured value, 6 times 10 to the negative 10th joules per cubic meter, is what quantum field theory was supposed to predict. Except it didn't. It predicted 10 to the 113, or depending on your cutoff and your assumptions, something even larger. The disagreement is not close. It's not a factor of 2 or 10 or even a million. It's a factor of 10 to the 120 something. A 1 followed by more than 100 zeros. This is not a rounding error. This is not an overlooked correction term. This is the kind of discrepancy that suggests something is fundamentally broken. Either quantum field theory is wrong about the vacuum energy, which seems unlikely given how well it predicts everything else, or general relativity is wrong about how vacuum energy gravitates, which seems equally unlikely given how well general relativity has been tested in every other context. Or there's some unknown symmetry, some cancellation mechanism, some new piece of physics that makes the enormous positive contributions from quantum fluctuations almost exactly cancel against some equally enormous negative contribution from somewhere else, almost exactly, but not quite, leaving behind a tiny residual that matches what we observe. Nobody knows what that mechanism is. Nobody has found a symmetry that does the job without breaking other things we know are true. And the more carefully you look at the problem, the worse it gets. Because the vacuum energy we observe is not just small, it's suspiciously small. If the true value were exactly 0, that would be interesting. 0 is special. 0 suggests a symmetry, a reason, an explanation. But the observed value is not 0. It's tiny but non-zero. Roughly 10 to the negative 123 in the natural units physicists use when they want to avoid writing out all the zeros. That's small enough to have escaped notice for most of cosmic history, but large enough to dominate the universe's dynamics today. Why that particular value? Why now? Why not 100 times larger or 100 times smaller? There are anthropic arguments. Some physicists suggest that if the vacuum energy were much larger, the universe would have expanded so fast that galaxies never formed, stars never ignited, life never appeared. We observe a small cosmological constant because only in a universe with a small cosmological constant could observers exist to measure it. That logic has a certain appeal. It also has a certain desperation. It replaces a prediction with a selection effect. It tells you why the value couldn't be much larger without telling you why it is what it is. The vacuum catastrophe is not just a problem for theorists trying to make their equations match. It's a crack in the foundation. We have two theories, quantum field theory and general relativity, that each work beautifully within their own domains. Quantum field theory describes particles and forces and predicts experimental results to absurd precision. General relativity describes space-time and gravity and has passed every test we've thrown at it for more than a century. But when you try to combine them, when you ask what the energy of empty space should be according to quantum field theory, and then ask what effect that energy should have according to general relativity, the answer you get is nonsense. The vacuum should weigh so much that space itself would curl up into a ball smaller than an atom. It doesn't. Space is vast and nearly flat. The vacuum energy we observe is real, measurable, and cosmologically significant, but it's more than 100 orders of magnitude smaller than our best theories predict. That gap is not going away. It's been sitting in plain sight for decades. And the deeper physicists dig, the more it looks like the gap is telling us something important. Maybe the vacuum is more complicated than we thought. Maybe there are contributions we haven't accounted for, fields we haven't discovered, symmetries we haven't noticed. Or maybe the question itself is wrong. Maybe asking what the energy of empty space is doesn't have a single clean answer, the way asking for the mass of an electron does. Maybe the vacuum is not a state but a process, not a thing but a context, and the tools we're using to describe it are missing something essential. What we know for certain is that the vacuum is not empty. Quantum mechanics will not let it be empty. The uncertainty principle, the zero-point energy, the virtual particles flickering in and out of existence, all of it is real, measurable, verified in laboratories around the world through effects like the Casimir force and the Lamb shift and the anomalous magnetic moment. Empty space hums with activity. It has structure, energy, and consequences. And that energy, whatever its true value, is now the dominant driver of the universe's expansion. The vacuum is not passive, it is not inert, it is steering the fate of everything that exists. And we do not know why. The universe runs on credit, not the kind where you swipe a card and worry about the bill later, but something stranger and more fundamental. At the quantum level, energy can be borrowed from nothing, used for a fraction of a second, and paid back before anyone notices, except physicists did notice. They noticed because the things doing the borrowing left traces, not fingerprints exactly, more like shadows. Distortions in the fabric of reality that shouldn't be there if empty space were truly empty. And those shadows, when you measure them carefully, tell you that the vacuum is not just humming with activity, it's a bank. A bank that never closes, never runs out of funds, and operates according to rules that would make any accountant quit on the spot. The loan mechanism comes straight from Heisenberg's uncertainty principle, but applied to energy and time instead of position and momentum. The principle says that if you measure the energy of a system over an extremely short time interval, the uncertainty in that energy measurement can be enormous. Or flipped around, the shorter the time interval you're looking at, the larger the energy fluctuation you're allowed to have without violating any laws of physics. The equation that governs this is simple in structure. The uncertainty in energy multiplied by the uncertainty in time has to be greater than or equal to a very small number. That small number is Planck's constant divided by 4 pi, but the exact value doesn't matter for the picture. What matters is the relationship. Small time window, big energy uncertainty. Shrink the time window to nearly nothing, and the energy uncertainty can briefly become enormous. This is not a statement about measurement error. This is nature leaving a loophole. If you only need the energy for a tiny fraction of a second, you can borrow a huge amount. The universe will look the other way, but the loan has to be repaid almost immediately. The bigger the loan, the faster the repayment. Borrow a little energy, and you can keep it for a relatively long time before the books have to balance. Borrow a massive amount, and you've got a deadline measured in billionths of a second. Miss that deadline, and you'd be violating the uncertainty principle, which the universe does not allow. The loan gets repaid, always, automatically, built into the math. This is where virtual particles come from. The vacuum is filled with quantum fields. Every type of particle has its own field. Electron field, quark field, photon field, all of them overlapping, existing everywhere simultaneously. These fields are never truly at rest, even in their lowest energy state. Even when there are no real particles rippling through them, the fields fluctuate. And if a fluctuation is big enough and brief enough, it can create a particle. Not a permanent particle, a temporary one, a virtual one. The field borrows enough energy from the vacuum to produce a particle and its corresponding antiparticle, an electron and a positron, a quark and an antiquark, a photon that splits into an electron-positron pair and then recombines. These pairs exist for a moment so short you could never hope to catch one, and then annihilate. The particle and antiparticle collide, cancel each other out, and the borrowed energy gets returned to the vacuum. The field drops back to its ground state. The transaction completes, and an instant later, somewhere else, it happens again. This is not speculation. This is not a loose metaphor for something more complicated happening underneath. This is the operational description used by every working particle physicist. When you calculate how an electron scatters off a photon, you don't just draw a straight line from the initial state to the final state. You include all the possible intermediate steps, all the ways the electron could emit and reabsorb a virtual photon, all the ways the photon could split into a virtual electron-positron pair that recombines before anyone notices. You sum up every possible path, every possible fluctuation, every possible loan and repayment, and that sum, impossibly, gives you the right answer. Measure the scattering in a laboratory, and the prediction matches reality to 12 decimal places. The virtual particles are contributing. They're part of the calculation. They're doing something. But are they real? That question has caused more arguments than almost anything else in quantum mechanics. Feynman, who invented much of the machinery for calculating these processes, was careful to call them internal lines in diagrams, mathematical tools, bookkeeping devices that help you organize the calculation but don't necessarily correspond to anything you could point to in space-time and say that's a particle. On the other hand, the effects they produce are undeniably real. If you pretend virtual particles don't exist, if you leave them out of the calculation, your predictions are wrong, badly wrong. Include them, and the predictions work. So in what sense are they not real? The most honest answer is that virtual particles are real in their effects, but not in their existence. They're not things you could ever isolate, measure, or watch decay. They don't last long enough. They don't travel far enough. They live entirely within the error bars the uncertainty principle allows, but they change the properties of real particles moving through the vacuum. They shift energy levels in atoms. They alter the strength of forces. They produce pressures that can be measured with laboratory equipment sitting on a table. The vacuum is doing something. That something involves energy appearing and disappearing on timescales too short to track directly. Call it what you want, the phenomenon is there. One of the cleanest pieces of evidence is the Casimir effect, and it's worth walking through in detail because it's one of the few cases where vacuum energy does something you can see without a particle accelerator. Hendrik Casimir was a Dutch physicist working at Philips research labs in the late 1940s. He was thinking about colloidal suspensions, particles floating in a liquid, and trying to understand the forces between them. The mathematics led him into quantum field theory, and he noticed something strange. If you take two uncharged metal plates and place them very close together in a vacuum, the quantum vacuum itself should produce a force pulling the plates together. The reasoning goes like this. The vacuum is filled with virtual photons popping in and out of existence. These photons have wavelengths. Some are long, some are short. All wavelengths are present in the vacuum fluctuations. But if you put two metal plates extremely close together, Only certain wavelengths can fit in the gap between the plates. Wavelengths longer than the gap between the plates get excluded. They can't fit. They don't contribute to the vacuum energy in that region. Outside the plates, all wavelengths are allowed, so the vacuum energy density between the plates is slightly lower than the vacuum energy density outside the plates. That difference in energy density produces a net force. The higher energy vacuum outside pushes the plates together. Casimir calculated the force in 1948. He predicted it should be proportional to 1 over the distance between the plates raised to the 4th power. Extremely sensitive to distance. Bring the plates closer and the force grows rapidly. Push them apart and the force drops off fast. The force itself is tiny. For 2 plates, 1 square centimeter in area separated by 1 micrometer, the force is about 10 micronewtons. That's roughly the weight of a red blood cell pressing down on the plates, but it's measurable. And Casimir's colleague Dick Polder helped refine the calculation. In 1948, the technology to test it didn't exist. The plates had to be almost perfectly flat, almost perfectly parallel, and the distance between them had to be controlled to better than a micrometer while you measured forces smaller than anything a normal scale could detect. It took decades. The first convincing measurement came in 1958 when Marcus Spane, another Dutch physicist, managed to detect something consistent with the Casimir force, but with error bars so large he couldn't definitively confirm it. The real confirmation came in 1997 when Steve Lamoro at the University of Washington built an apparatus sensitive enough to measure the force with less than 5% uncertainty. He used a torsion pendulum, a tiny mirror mounted on a fine wire, and watched how the mirror twisted when a metal sphere was brought close to a flat plate. The force matched Casimir's prediction. Others repeated the experiment with better precision. By the early 2000s, the Casimir effect had been measured to better than 1% accuracy. The vacuum is pushing, exactly as predicted. This is not a force you can explain with classical physics. There are no charges on the plates. There's no light shining on them. There's no air between them. They're in a vacuum. The only thing that can account for the force is the difference in vacuum energy between the inside and the outside. Virtual photons that can't fit between the plates are contributing less to the energy density in that region than the virtual photons outside. The vacuum on the outside has more modes, more fluctuations, more zero-point energy, and that difference produces a measurable, repeatable, undeniable force. Empty space is not empty, it weighs something. And when you change the geometry, when you restrict which wavelengths can fluctuate in a given region, the weight changes and the difference pushes. There are variations of the effect. You can use different geometries, spheres instead of plates, cylinders, corrugated surfaces. The force changes depending on the shape, and the predictions match the measurements every time. You can even reverse the effect under certain conditions. Use materials with the right electromagnetic properties, and the Casimir force can become repulsive instead of attractive. The vacuum energy density between the plates becomes higher than the density outside, and the plates push apart. All of this confirms the same underlying picture. The vacuum is not passive, it's not a void. It's a dynamic background filled with quantum fluctuations, and those fluctuations have structure, energy, and consequences. Another way to see vacuum effects is through the self-energy of particles. Every charged particle, say an electron, generates an electric field. That field extends outward in all directions. Classically, the energy stored in that field is finite as long as the particle has some finite size. But quantum mechanically, the electron appears to be a point particle. No size, no internal structure, just a point. and a point charge generates an electric field that grows stronger and stronger as you get closer to the charge, all the way down to zero distance. The energy stored in that field, if you integrate it all the way to the center, diverges. It goes to infinity. That's a problem. The electron doesn't have infinite energy. It has a well-defined mass, about 9 times 10 to the negative 31 kilograms. That's a finite number, and you can measure it. So, where's the infinity hiding? The answer is that the electron's measured mass includes contributions from the vacuum. The bare electron, the hypothetical particle without any interaction with the vacuum, might have one value of mass. But the electron is never isolated from the vacuum. It's constantly emitting and reabsorbing virtual photons. Those photons briefly fluctuate into virtual electron-positron pairs. Those pairs interact with the original electron. All of that activity contributes to what we measure as the electron's mass. The infinity from the self-energy of the bare charge gets absorbed into a redefinition of the mass. Physicists call this renormalization. You start with an equation that predicts infinity. You carefully reorganize the math, moving the infinite part into a redefinition of a parameter like mass or charge, and what's left over are finite, measurable, predictable corrections. And those corrections match experiments. This is not a trick. Or rather, it is a trick, but it's a trick that works. Renormalization was controversial when it was first introduced in the late 1940s. Some of the greatest physicists of the era, including Dirac, hated it. Dirac called it ugly. He thought it was sweeping infinities under the rug instead of solving the real problem. But the predictions were too good to ignore. Quantum electrodynamics, the theory of how electrons and photons interact, gives predictions that match measurements to a precision unmatched by any other theory in history. The anomalous magnetic moment of the electron, calculated including all the virtual particle corrections, agrees with experiment to 12 decimal places. You don't get that kind of agreement by accident. The virtual particles are doing something. The vacuum is contributing. And the infinities, once you handle them carefully, go away. The same pattern shows up in other forces. Quantum chromodynamics, the theory of the strong force that holds quarks together inside protons and neutrons, has its own vacuum fluctuations. Gluons, the particles that carry the strong force, can split into virtual quark-antiquark pairs. Those pairs screen the color charge of the quarks, making the force weaker at short distances and stronger at long distances. This is called asymptotic freedom, and it's why you can never pull a single quark out of a proton. Try to separate two quarks, and the energy you're pumping into the system eventually becomes large enough to create new quark-antiquark pairs out of the vacuum. Instead of pulling one quark free, you end up creating new particles. The vacuum itself resists the separation. It's cheaper, energetically, to create new particles than to pull the old ones apart. The vacuum mediates the force. Even gravity, at least in principle, should have vacuum fluctuations. Gravitons, the hypothetical particles that would carry the gravitational force in a quantum theory of gravity, should appear and disappear in the vacuum just like photons and gluons. We've never detected a graviton. Gravity is so weak compared to the other forces that quantum gravitational effects are almost impossible to measure directly. But if quantum mechanics applies to gravity the way it applies to everything else, and there's no reason to think it doesn't, then space-time itself should be fluctuating at the smallest scales. At distances around the Planck length, about 10 to the negative 35 meters, space-time should be foaming, fluctuating, anything but smooth. The geometry of the universe at that scale should look less like a sheet and more like a sea in a storm. We can't see that far down. We can't probe distances that small. But the math says it should be happening. All of this paints a picture of the vacuum as an active participant in physics, not a stage where particles perform, a dynamic entity that contributes to every interaction. Virtual particles mediate forces. Vacuum fluctuations shift energy levels. The Casimir effect produces measurable pressures. The vacuum is not nothing. It's the baseline, the ground state, the lowest energy configuration of all fields. And even in that state, it has energy. A lot of energy, according to the calculations. Every mode of every field contributes a bit of zero-point energy. Add them all up, and the total is staggering. This is where things start to go wrong. Because if every mode contributes, and there are infinitely many modes, one for every possible wavelength, then the sum diverges again. Infinity. Physicists try to tame the infinity by imposing a cutoff. They say, fine, we'll only count modes up to some maximum frequency. Above that frequency, something else happens. New physics, a breakdown of quantum field theory. Whatever it is, it makes the sum stop growing. The question is where to put the cutoff. The natural choice is the Planck scale, the energy scale where quantum gravity effects are expected to matter. That's about 10 to the 19 giga-electron volts. It's the highest energy scale where we have any reason to trust our current theories. If you cut off the sum at the Planck scale and calculate the vacuum energy density, you get a number around 10 to the 113 joules per cubic meter. That's the energy density of the quantum vacuum, according to quantum field theory, with a reasonable cutoff. Now compare that to what we actually observe. Cosmological measurements using supernova data and the cosmic microwave background and the large-scale structure of the universe tell us the vacuum energy density is about 5 times 10 to the negative 10 joules per cubic meter, not 10 to the 113, 10 to the negative 10. The prediction is bigger than the observation by a factor of about 10 to the 123. That's a 1 followed by 123 zeros. The theoretical prediction is more than 100 orders of magnitude too large. This is not a small error. This is not something you can fix with a better calculation or a more careful measurement. This is a catastrophic failure. If the vacuum energy density were really as large as quantum field theory predicts, the gravitational effect of that energy would dominate everything. Space would curve so violently that the universe would have collapsed into a singularity or exploded outward so fast that no structures could form. Galaxies wouldn't exist, stars wouldn't exist, atoms wouldn't exist. There would be no time for anything to happen before the universe tore itself apart. But the universe is nearly 14 billion years old. Galaxies fill the sky, stars burn steadily for billions of years, matter is stable, the vacuum energy we observe is tiny, barely there. Just enough to make the expansion of the universe accelerate very gently, nothing like the catastrophe the equations predict. Something is wrong. Either quantum field theory is wildly wrong about the vacuum energy, which seems unlikely given how well it predicts everything else, or general relativity is wildly wrong about how vacuum energy gravitates, which seems equally unlikely given how well general relativity has been tested. Or there's some unknown mechanism, some symmetry, some cancellation that makes the enormous positive contributions from all the quantum modes almost exactly cancel against something else. Almost exactly, but not quite, leaving behind a tiny residual that matches the observed cosmological constant. Nobody knows what that mechanism is. Nobody has found a symmetry that works without breaking other things. And the longer the problem sits unsolved, the more uncomfortable it becomes. The vacuum is real, the energy is real, The effects are measurable. The Casimir force exists, the Lamb shift exists. The anomalous magnetic moment of the electron matches theory to absurd precision. All of that requires the vacuum to have structure and energy, virtual particles flickering in and out of existence, zero-point energy humming at the foundation of every field, the universe borrowing from itself, constantly, on timescales too short to notice directly, but long enough to leave marks. Empty space is not empty, it's full, and what it's full of should have destroyed the universe before it began. It didn't. We're here. The stars are shining. And the discrepancy between what should be and what is stands as the single largest unsolved problem in fundamental physics. A gap not of a few percent, but of more than 100 orders of magnitude. The worst prediction ever made. And the question is not whether the vacuum has energy. The question is why the energy we measure is so impossibly, inexplicably, absurdly small. The numbers were bad. Not wrong answer on a homework assignment bad. Not off by a factor of 2 bad. The kind of bad that makes you check your calculator, rerun the simulation, and then walk away from your desk, hoping the problem will solve itself overnight. Except it didn't solve itself overnight. It's been sitting there for decades, getting worse every time someone tries to fix it. The vacuum energy density predicted by quantum field theory is roughly 10 to the 113th joules per cubic meter. The vacuum energy density we actually measure in the universe is about 5 times 10 to the negative 10th joules per cubic meter. The ratio between those two numbers is approximately 10 to the 123. That's not a typo. That's not a misplaced decimal. The theoretical prediction is bigger than the observed value by more than 120 orders of magnitude. That's a 1 followed by 123 zeros. It is, by any reasonable measure, the worst prediction in the history of science. Before we appreciate just how spectacularly wrong that is, we need to understand how physicists arrived at the prediction in the first place. Because it wasn't a guess. It wasn't pulled from thin air. It was a straightforward calculation using quantum field theory, the same framework that predicts the anomalous magnetic moment of the electron to 12 decimal places. The same theory that's been tested more rigorously than any other in the history of physics. The same theory that works perfectly for everything else we've ever asked it to explain. And then you ask it one more question. What's the energy density of empty space? And it gives you an answer so absurdly large that if it were correct, the universe would have destroyed itself a fraction of a second after the Big Bang. Here's the calculation, step by step. Start with a quantum field. Any field, the electron field, the photon field, doesn't matter. Every field in the universe, according to quantum mechanics, can be thought of as a collection of harmonic oscillators, one at every point in space. A harmonic oscillator is just a system that oscillates like a spring or a pendulum. The quantum version has discrete energy levels. It can have 1 quantum of energy, 2 quanta, 3 quanta, and so on, but it can never have 0 energy. Even in its lowest energy state, the ground state, it still has half a quantum of energy left over. That's the 0-point energy. The oscillator can never stop moving. The uncertainty principle won't let it. Now extend that to a field filling all of space. At every point, at every possible wavelength, there's a mode of the field that can oscillate. Short wavelengths, high frequencies. Long wavelengths, low frequencies. Each mode is its own harmonic oscillator, and each one contributes half a quantum of 0-point energy. To find the total vacuum energy density, you sum up the contributions from all the modes, all the wavelengths, all the frequencies. from the longest waves stretching across the observable universe down to the shortest waves your theory can handle. And that sum, if you take it seriously, diverges. It goes to infinity. Infinity is not a number you can measure, so physicists impose a cutoff. They say, fine, we'll only count modes up to some maximum frequency. Above that, something happens, new physics, a breakdown of quantum field theory. Maybe quantum gravity kicks in. Maybe the structure of space-time itself changes at extremely short distances. We don't know. But we know quantum field theory can't be the whole story at arbitrarily high energies, so we cut the sum off somewhere reasonable and see what we get. The most natural place to impose the cutoff is the Planck scale. That's the energy scale, about 10 to the 19th giga-electron-volts, where the gravitational interaction between two particles becomes as strong as the other fundamental forces. It's the scale where space-time itself is expected to fluctuate quantum mechanically, where the smooth geometry of general relativity breaks down into something stranger. We have no experiments that probe anywhere close to the Planck scale. The Large Hadron Collider reaches energies around 10 to the 4 giga-electron-volts, more than 10 trillion times weaker. But the Planck scale is where our current theories hit a wall. It's the natural place to stop the calculation, cut off the sum at the Planck scale and add up all the contributions from every mode of every field up to that frequency. The answer you get is a vacuum energy density of roughly 10 to the 113th joules per cubic meter. That number is so large, it's hard to grasp intuitively. For comparison, the energy density of solid matter, like lead, is about 10 to the 17 joules per cubic meter if you convert the mass into energy using E equals mc squared. The vacuum, according to this calculation, should have an energy density nearly 100 trillion times greater than lead. Every cubic meter of empty space should weigh more, in energy terms, than a trillion kilograms of matter. If that were true, the universe would not look anything like it does. Energy, all energy, gravitates according to general relativity. A large enough energy density curves space-time. An energy density of 10 to the 113th joules per cubic meter would curve space-time so violently that the universe would not be able to expand in any recognizable way. Depending on the sign of the energy, space would either collapse into a singularity almost immediately or explode outward so fast that matter couldn't clump together into anything. No galaxies, no stars, no planets, no atoms lasting long enough to form molecules. The universe would be over before it started. Except the universe is not over. It's nearly 14 billion years old. Galaxies are scattered across billions of light years. Stars have been burning steadily for billions of years. Matter is stable. The vacuum energy density we actually observe, inferred from cosmological measurements of how fast the universe is expanding, is about 5 times 10 to the negative 10th joules per cubic meter, not 10 to the 113, 10 to the negative 10. The predicted value is larger than the observed value by a factor of about 10 to the 123, depending on whose calculation you use and where exactly you set the cutoff. Some estimates put it at 10 to the 120, others at 10 to the 122. The exact number doesn't matter. The point is the discrepancy is not small. It's not even close. It's the largest mismatch between theory and experiment ever recorded in any branch of science. Let's put that in perspective. The worst predictions in the history of physics before this were off by factors of maybe 2, maybe 10, occasionally 100 if the theory was really crude. When Lord Kelvin tried to estimate the age of the Earth using thermodynamics in the late 1800s, he got it wrong by about a factor of 100. He calculated tens of millions of years. The real answer is closer to 4.5 billion. Big error. Embarrassing error. But it was a factor of 100. The vacuum catastrophe is a factor of 10 to the 120. If Kelvin's error were scaled up to match the vacuum catastrophe, his estimate for the age of the Earth would have been off by more than the age of the universe raised to the 20th power. That's not an error. That's a theory breaking in your hands, and it gets worse. Because the prediction isn't just wrong. It's wrong in a way that makes you question whether you understand anything at all. Quantum field theory works. It works beautifully. You can calculate scattering cross-sections for particles colliding in accelerators, and the predictions match experiments to absurd precision. You can calculate the energy levels of atoms, and the answers agree with measurements to 10 or 12 decimal places. You can predict the rate at which particles decay, and you're right, over and over, to extraordinary accuracy. Every test of quantum field theory in every domain where we can test it says the theory is correct, the math is right, the framework is sound, general relativity works too. You can calculate the orbit of Mercury, and the prediction matches observations so precisely that it explained a discrepancy that had baffled astronomers for decades. You can predict the bending of light around the sun, and the measurement matches the theory exactly. You can predict the existence of black holes, gravitational waves, the expansion of the universe, and all of it checks out. Every test of general relativity in every regime where we can test it says the theory is correct. The geometry of space-time really does curve in response to energy and momentum. Gravity really is the curvature of space-time. Both theories work, and when you ask them a simple question, what's the energy of empty space and how does that energy affect the expansion of the universe, they give you an answer that's off by more than 100 orders of magnitude. That's not a rounding error. That's not an overlooked correction. That's a signal that something fundamental is broken. Either quantum field theory is completely wrong about vacuum energy, despite being right about everything else, or general relativity is completely wrong about how vacuum energy gravitates, despite being right about everything else. Or there's a third option, which is that both theories are right, but there's some unknown mechanism that cancels the enormous vacuum energy predicted by quantum field theory down to the tiny value we observe, almost perfectly, leaving behind a residual that just happens to match the cosmological constant. That third option is what most physicists bet on, but nobody knows what the mechanism is. Nobody has found a symmetry or a field or a new principle that does the job without breaking something else we know is true. The most popular candidate for decades was supersymmetry, a hypothetical symmetry that pairs every particle with a partner particle of opposite spin. In a perfectly supersymmetric universe, the vacuum energy contributions from particles and their superpartners would cancel exactly. The vacuum energy density would be zero. Problem solved, except the universe is not perfectly supersymmetric. If it were, we'd have seen the superpartners by now. Every electron would have a selectron, every quark would have a squark, every photon would have a photino. None of them have been detected. The Large Hadron Collider has searched extensively. Nothing. If supersymmetry exists, it's broken. The symmetry holds at extremely high energies, maybe near the Planck scale, but at the energies we can access, it's gone. And if supersymmetry is broken, the cancellation is incomplete. The vacuum energy density is no longer zero. It's something. And the something you get from broken supersymmetry, depending on how and when the symmetry broke, is still way too large. off by dozens of orders of magnitude. Better than 120, maybe, but not good enough. Not even close to good enough. Some physicists have tried anthropic arguments. The idea is that the vacuum energy density varies from place to place in a vast multiverse, and we happen to live in a region where it's small, because only in regions with small vacuum energy can galaxies form, stars ignite, and observers evolve to ask the question. If the vacuum energy were much larger, the universe would have expanded too fast for structure to form. If it were much smaller and negative, the universe would have collapsed before anything interesting happened. We observe a small positive value because we couldn't exist in a universe with any other value. That logic has a certain appeal, but it's not a prediction. It's a selection effect. It replaces the question, why is the vacuum energy this value, with the answer because if it weren't, we wouldn't be here to ask. That might be true, but it doesn't feel like progress. It feels like giving up. Others have suggested that maybe general relativity needs to be modified. Maybe vacuum energy doesn't gravitate the way ordinary energy does. Maybe there's a term in Einstein's equations that we're missing, something that cancels the gravitational effect of the vacuum. That's possible, but it's hard to see how you'd write down such a term without breaking everything else general relativity gets right. Gravity couples to all forms of energy and momentum. That's a core principle. You can't just tell vacuum energy to sit in the corner and not participate. If you modify the equations to make vacuum energy not gravitate, you risk changing how ordinary matter gravitates too. And we've tested how ordinary matter gravitates very, very carefully. The theory works. Any modification has to be extraordinarily fine-tuned to leave all the successes intact while fixing the one catastrophic failure. The problem is not just that the prediction is wrong. The problem is that the prediction is so wrong it makes you doubt the entire framework. Quantum field theory and general relativity are the two pillars of modern physics. Everything we know about particles, forces, matter, energy, spacetime, and gravity rests on these two theories. They've been tested more thoroughly than any other scientific theories in history, and they give wildly incompatible answers to a question as basic as what's the energy of empty space. That incompatibility is not a minor technical issue, it's a crack in the foundation. There's a number that gets thrown around a lot in popular accounts of this problem, and it's worth pausing to make sure it's clear where it comes from. The factor of 10 to the 120, or 10 to the 123 depending on who's counting, is the ratio between the predicted vacuum energy density and the observed vacuum energy density. The predicted value comes from summing up zero-point energies of quantum fields with a cutoff at the Planck scale. The observed value comes from measuring the cosmological constant using supernova data, cosmic microwave background measurements, and large-scale structure surveys. Both numbers are reasonably well established. The prediction is about 10 to the 113 joules per cubic meter. The observation is about 10 to the negative 10 joules per cubic meter. Divide one by the other and you get 10 to the 123. But here's the uncomfortable part. The exact size of the discrepancy depends on your assumptions. If you set the cutoff lower, say at the scale of electroweak symmetry breaking instead of the Planck scale, the predicted value drops. Not enough to fix the problem, but enough to change the discrepancy from 10 to the 120 to maybe 10 to the 60. Still catastrophically large, still the worst prediction in science, but not quite as bad. On the other hand, if you trust quantum field theory all the way up to the Planck scale, the discrepancy is worse. Some calculations, depending on how you regularize the sum and which fields you include, give even larger predictions. The error could be 10 to the 125. The point is, the exact number is negotiable. The catastrophe is not. And there's another layer to the disaster. The vacuum energy we observe is not zero. If it were zero, that would be interesting. Zero is a special number. Zero suggests a symmetry, a reason, an explanation. If the vacuum energy density were exactly zero, you could argue that some unknown principle sets it to zero, and the problem would be, if not solved, at least framed in a way that suggests where to look for an answer. But the observed value is not zero. It's tiny, but it's definitely non-zero. About 10 to the negative 123 in the natural units physicists use. That's small enough to have been irrelevant for most of the universe's history. For the first 10 billion years, the vacuum energy density was negligible compared to the density of matter and radiation. Only in the last few billion years, as matter spread out and its density dropped, did vacuum energy start to dominate. We're living in the era when dark energy, the name cosmologists use for the mysterious stuff causing the accelerated expansion, has just taken over. If the cosmological constant were 10 times larger, galaxies would have been ripped apart before life had time to evolve. If it were 10 times smaller, we wouldn't have noticed it yet. The value we observe is in a narrow window where it's just becoming important. Why? Why this value? Why now? There's no good answer. Physicists have been chewing on this problem since the late 1960s, when cosmological observations started to put limits on the cosmological constant. The vacuum catastrophe became a full-blown crisis in the 1990s, when supernova observations confirmed that the expansion of the universe is accelerating, and the energy density driving that acceleration matches what you'd get from a small positive cosmological constant. Since then, the data has only gotten better. The value is well measured. The theoretical prediction is well calculated. The discrepancy is real, and it's not going away. Some of the best minds in physics have attacked this problem. Nobel laureates have spent years trying to crack it. Entire conferences have been devoted to it. Papers proposing solutions pile up by the hundreds, and none of the solutions work. Every proposed mechanism either doesn't solve the problem, or solves the problem by breaking something else, or requires fine-tuning so extreme that it just replaces one mystery with another. The vacuum catastrophe is still sitting there, unsolved, unresolved, and getting more embarrassing every year that passes without an answer. Here's what makes it particularly galling. The vacuum energy is real. It's not a theoretical curiosity. It's measured. The cosmological constant shows up in the equations governing the expansion of the universe, and its value has been measured to a few % precision using multiple independent methods. Supernova observations, cosmic microwave background data, baryon acoustic oscillations in the large-scale structure of the universe, all of them point to the same number. Dark energy makes up about 68% of the total energy budget of the universe. It's the single largest component, bigger than dark matter, bigger than ordinary matter, bigger than radiation. The universe is mostly vacuum energy. And we have no idea why the amount we observe is so absurdly, impossibly, inexplicably smaller than what the equations predict. This is not a problem you can ignore. It's not a loose end you can tie up later. It's a fundamental breakdown of our understanding. Quantum field theory says the vacuum has a certain energy. General relativity says that energy should curve space-time. Put the two together and you get a universe that shouldn't exist. But the universe does exist. The prediction is wrong, spectacularly wrong, 120 orders of magnitude wrong. And until someone figures out why, we're stuck with the reality that our two best theories, the two pillars holding up all of modern physics, are giving us an answer that makes no sense. The vacuum catastrophe is not just the worst prediction in the history of science. It's a sign that we're missing something, something big, something that changes the picture at a level we haven't reached yet. Maybe there's a symmetry we haven't noticed. Maybe there's a field we haven't discovered. Maybe the vacuum itself is more complicated than we thought, layered with structure and dynamics we can't see from here. Or maybe the entire framework, quantum field theory plus general relativity, is just an approximation that works beautifully in the regimes we've tested, but breaks down when you ask it about the energy of empty space. Maybe there's a deeper theory underneath, a theory of quantum gravity or something else entirely that makes the catastrophe go away. We don't know. And until we do, the discrepancy stands as a monument to our ignorance. A reminder that for all the progress we've made, for all the precision and predictive power of modern physics, we still don't understand what empty space is, what energy is, or why the universe is the way it is, instead of collapsing into nothing the moment it began. The problem sitting on physicists' desks was not just theoretical. It wasn't just an equation that didn't balance, or a calculation that produced an ugly answer you could sweep under the rug and ignore. The problem had consequences, real ones, observable ones. The vacuum energy density predicted by quantum field theory was 10 to the power of 123 times larger than what anyone measured. That's bad. That's catastrophically bad. But here's what makes it worse. The universe is actually doing something that looks an awful lot like vacuum energy at work. Space itself is expanding. Not just expanding the way it's been expanding for nearly 14 billion years, coasting outward from the Big Bang, accelerating. Galaxies are moving apart faster and faster. Something is pushing space outward with more and more force as time goes on. And the best explanation anyone has for what that something is happens to be the same vacuum energy that the equations get so spectacularly wrong. The universe is telling us vacuum energy is real and important and currently running the show. The equations are telling us vacuum energy should have destroyed everything before it started. Both statements are true, and nobody knows how to make them fit together. Let's start with expansion itself, because that's where the modern story begins. The universe is getting bigger. Every galaxy outside our local gravitational neighborhood is moving away from us. The farther away a galaxy is, the faster it's receding. This is Hubble's law, named after Edwin Hubble, the astronomer who first measured it convincingly in 1929. Hubble wasn't the first to notice that distant galaxies had redshifts, meaning their light was stretched toward longer wavelengths, shifted toward the red end of the spectrum. Others had seen that. But Hubble was the first to show that the amount of redshift increased with distance in a clean linear relationship. Twice as far away, twice the redshift. 3 times as far, 3 times the redshift. The pattern was unmistakable. The universe was expanding. This was not what anyone expected. Einstein had published general relativity in 1915, and when he applied his equations to the universe as a whole, he found something uncomfortable. The equations didn't allow for a static universe. Space couldn't just sit still. It either had to expand or contract. Einstein didn't like that. Everyone at the time assumed the universe was eternal and unchanging on the largest scales. Stars moved, galaxies might drift, but the overall structure of space was supposed to be fixed. So Einstein added a term to his equations, a cosmological constant, specifically designed to counteract the tendency of space to collapse under its own gravity. The constant produced a kind of repulsive effect that exactly balanced the attractive pull of matter, holding the universe in a steady state. It was an ugly fix. Einstein knew it, but it worked mathematically. The equations allowed for a static universe If you included the constant, then Hubble showed the universe wasn't static. Galaxies were moving apart, space was expanding. Einstein reportedly called the cosmological constant his biggest blunder. If he'd trusted his equations, if he'd left the constant out, general relativity would have predicted the expansion of the universe more than a decade before anyone observed it. That would have been one of the greatest predictions in the history of science. Instead, he added a fudge factor to make the theory match an assumption that turned out to be wrong. The constant was discarded. The universe was expanding, and the expansion was enough to explain why space wasn't collapsing. No extra term needed. For most of the 20th century, that's where things sat. The universe started with a big bang. Space has been expanding ever since, carrying galaxies along with it like raisins in rising bread dough. The big question was whether the expansion would continue forever or eventually reverse. That depended on the density of matter in the universe. If there was enough matter, gravity would eventually win, slow the expansion to a stop, and pull everything back into a big crunch. If there wasn't enough matter, the expansion would continue forever, gradually slowing but never quite stopping. Right on the edge, you'd get a flat universe, expanding forever but decelerating at just the right rate. Cosmologists spent decades trying to measure the density of matter precisely enough to figure out which scenario we were in. Then, in 1998, two independent teams of astronomers studying distant supernovae announced results that made no sense. They were using a specific type of exploding star, called a Type Ia supernova, as a standard candle. Type Ia supernovae are useful because they all explode with roughly the same peak brightness. If you know how bright a supernova truly is, and you measure how bright it looks from Earth, you can calculate how far away it is. Combine that distance with the redshift of the galaxy hosting the supernova, and you can map out the expansion history of the universe. How fast space was expanding in the past, compared to how fast it's expanding now. The expectation was that the expansion should be slowing down. Gravity pulls everything together. The expansion, leftover momentum from the Big Bang, should be fighting against gravity and losing. Slowly, but losing. The distant supernovae, whose light has been traveling for billions of years, should look slightly closer than you'd expect if the universe were expanding at a constant rate. Because the expansion was faster back then and has been slowing ever since. The supernovae looked farther away, not closer, farther. The expansion rate in the past was slower than the expansion rate today. Space is not coasting. It's accelerating. Galaxies are moving apart faster now than they were billions of years ago. Something is pushing them. Something with enough energy to overcome the gravitational pull of all the matter in the universe and still have enough left over to keep accelerating the expansion. The discovery was so unexpected that both teams checked and rechecked their data, looking for errors. There weren't any. The universe is speeding up. That discovery won the Nobel Prize in 2011, and it created a problem. Acceleration requires energy, a lot of energy, and the energy has to be spread uniformly throughout space, not clumped into galaxies or clouds of gas. If it were clumped, it would slow down the expansion in some regions and speed it up in others. The acceleration is smooth. Every part of space is expanding at the same rate, so the energy driving it has to be everywhere, evenly distributed, and it has to have a very specific property. It has to have negative pressure, positive energy density but negative pressure. That's the only combination that produces a repulsive gravitational effect in general relativity. Normal matter has positive pressure. Squeeze it and it pushes back. Radiation has positive pressure too. But vacuum energy, the energy of empty space, has negative pressure. It's a property baked into the math. If you take the equations of general relativity and ask what kind of substance could cause space to accelerate, the answer is something with an equation of state where the pressure is exactly equal to the negative of the energy density. That's not a common property. Most forms of energy don't behave that way, but vacuum energy does. By definition, a cosmological constant, interpreted as the energy density of empty space, produces exactly the kind of acceleration the supernova data showed. The simplest explanation for dark energy, the name cosmologists gave to whatever is causing the acceleration, is that it's vacuum energy, the cosmological constant, the same term Einstein added to his equations and then discarded as a blunder. Except it's not a blunder, it's real, it's there, and it's running the universe. Here's where the disaster compounds. The amount of dark energy required to explain the observed acceleration is well measured. You can calculate it from the supernova data, from observations of the cosmic microwave background, from the large-scale structure of galaxies. All three methods agree. The energy density of dark energy is about 5.96 times 10 to the negative 27 kilograms per cubic meter. Convert that to energy using E equals mc squared, and you get about 5.36 times 10 to the negative 10 joules per cubic meter. That's the vacuum energy density of the universe, measured, confirmed, sitting right there in multiple independent datasets. And it matches the behavior of a cosmological constant beautifully. Dark energy doesn't clump. It doesn't dilute as the universe expands. Its density stays constant even as space stretches. That's weird. Normal matter spreads out when space expands. Double the volume and the density drops by half. Radiation dilutes even faster because the wavelengths of photons get stretched as space expands, so each photon loses energy. But dark energy doesn't dilute. Its density is the same today as it was a billion years ago, as it will be a billion years from now. That's exactly what you'd expect if dark energy is the energy of space itself. Add more space, and you add more vacuum energy in direct proportion. The density stays constant. The total amount of energy in the universe increases as space expands. That sounds like it violates energy conservation. And, in a sense, it does, but general relativity allows it. Energy conservation in an expanding universe is more subtle than energy conservation in a fixed space. The equations permit the total energy to change if space itself is changing. And if dark energy is vacuum energy, that's what happens. So observationally, dark energy looks like vacuum energy. It has the right equation of state. It has the right behavior as the universe expands. It has the right distribution, smooth and uniform across all of space. The fit is nearly perfect, and the amount of dark energy we observe, 5 times 10 to the negative 10 joules per cubic meter, is enormous by cosmological standards. It's the dominant component of the universe's energy budget. About 68% of the total. Dark matter makes up about 27%. Ordinary matter, stars and planets and gas and dust and everything made of atoms, is less than 5%. The universe is mostly dark energy, mostly vacuum, and vacuum energy is currently in control of what happens next. Whether the universe expands forever, whether galaxies eventually lose sight of each other as space stretches too fast for light to cross the gaps, all of that is determined by the vacuum. But here's the knife twist. The vacuum energy density predicted by quantum field theory is about 10 to the 113th joules per cubic meter. The vacuum energy density we observe is about 10 to the negative 10 joules per cubic meter. The prediction is 10 to the 123 times too large. Dark energy explains the acceleration perfectly. The cosmological constant works. The observations fit. But the theory that's supposed to tell you what the cosmological constant should be gives you an answer that's off by more than 100 orders of magnitude. You have a model that matches the data beautifully, and a calculation that predicts the model should have destroyed the universe. Both are true, and they can't both be true. Let's make this concrete because the numbers are so extreme they lose meaning if you don't ground them. The observed vacuum energy density is about 5 times 10 to the negative 10 joules per cubic meter. That's tiny. To give you a sense of scale, a cubic meter of air at sea level has a mass of about 1.2 kilograms. Convert that to energy, and it's about 10 to the 17 joules. The vacuum energy in a cubic meter of space is about 10 to the negative 10 joules. The energy content of the vacuum is 100 trillion times smaller than the energy content of the air filling the same volume. The vacuum is, by any everyday standard, empty. Its energy density is negligible. Except on cosmological scales, it's not negligible. It's dominant. Because space is big, really big. The observable universe contains about 10 to the 80 cubic meters of space. Multiply that by the vacuum energy density and you get a total dark energy content of about 10 to the 70 joules. That's more energy than all the stars in all the galaxies in the observable universe combined. The vacuum outweighs everything else. And that tiny, almost negligible energy density per cubic meter, when you add it up across the entire cosmos, is enough to accelerate the expansion of space itself. Now, compare that to the prediction. Quantum field theory says the vacuum energy density should be about 10 to the 113th joules per cubic meter. If that were true, the total dark energy content of the observable universe would be about 10 to the 193 joules. That number is so large, it's meaningless. For comparison, the total mass energy of all the matter in the observable universe, converted using E equals mc squared, is about 10 to the 70 joules. The predicted vacuum energy is 10 to the 123 times larger than that. A universe with that much vacuum energy wouldn't expand gently over billions of years. It would explode. Space would double in size every 10 to the negative 43 seconds. That's the Planck time, the shortest interval of time that has any meaning in physics. The universe wouldn't last long enough for light to cross the diameter of a proton. There would be no time for particles to form, let alone stars or galaxies or anything resembling structure. The vacuum would tear everything apart faster than the speed of light, which is allowed because it's space itself expanding, not objects moving through space. Expansion can be as fast as it wants. And with a vacuum energy density of 10 to the 113th joules per cubic meter, expansion would be catastrophically, instantly, unimaginably fast. That didn't happen. The universe is nearly 14 billion years old. The expansion has been relatively gentle for most of that time. Only in the last few billion years has dark energy started to dominate, and even now, the acceleration is mild. Space is expanding at a rate of about 70 kilometers per second per megaparsec. A megaparsec is about 3.3 million light-years, so for every 3.3 million light-years you look outward, galaxies are receding 70 kilometers per second faster. That's a measurable effect, but it's not violent. It's not tearing galaxies apart. It's not ripping atoms apart. It's just gently, steadily accelerating the separation between distant structures. The universe is calm. The vacuum energy we observe is tiny, and the vacuum energy we calculate should have destroyed everything. This is the cosmic connection. Dark energy is real. Its effects are observed. Its density is measured. Its properties match what you'd expect from vacuum energy. The cosmological constant works as an explanation for why the universe is accelerating. But the cosmological constant is supposed to be the vacuum energy density predicted by quantum field theory, and that prediction is wrong by more than 100 orders of magnitude. The theory explains the phenomenon. The theory predicts the phenomenon should be 100 orders of magnitude stronger. Both statements come from the same framework. Both are unavoidable conclusions if you take the physics seriously, and they contradict each other so completely that it's hard to see how they could both be even approximately correct. There's another layer to this. The vacuum energy density we observe is not just small. It's small in a very specific way. It's small enough that for most of the universe's history, it didn't matter. In the early universe, radiation dominated. The energy density of photons was enormous, much larger than the energy density of matter or dark energy. As the universe expanded, radiation diluted faster than matter. Eventually, matter took over. For billions of years, the universe was matter-dominated. Galaxies formed, stars ignited. Structure grew, and all the while, dark energy was there, sitting quietly in the background, its density unchanging while everything else diluted. Then, a few billion years ago, the density of matter dropped below the density of dark energy. Dark energy started to dominate. The expansion started to accelerate. We're living in the transition era. The era when dark energy has just taken over and the universe has just started accelerating. A few billion years from now, dark energy will dominate so completely that the expansion will be exponential. Distant galaxies will disappear beyond the horizon as space stretches faster than light can cross it. But we're not there yet. We're right at the moment when dark energy becomes important. That timing is suspicious. Why now? Why is the vacuum energy density just small enough that it only started to matter in the last few billion years? If it were 10 times larger, it would have dominated much earlier, ripping apart galaxies before life had time to evolve. If it were 10 times smaller, it wouldn't dominate yet. We'd still be in a matter-dominated universe, and we wouldn't have noticed the acceleration. The value we observe is in a narrow window, and we happen to be living in the narrow window of time when that value matters. Coincidence? Maybe. Or maybe there's a selection effect. Maybe observers can only exist in universes where the vacuum energy density is small enough to allow structure to form, and large enough that it starts to dominate after structure has had time to develop. That's an anthropic argument. It doesn't explain why the value is what it is. It just says we couldn't observe any other value because we wouldn't exist. That might be true, but it doesn't feel like an answer. It feels like giving up. Here's what we know for certain. The universe is accelerating. That acceleration requires energy. The energy has to be smoothly distributed. It has to have negative pressure. It has to stay constant in density as space expands. Dark energy fits all of those requirements. The simplest explanation for dark energy is that it's vacuum energy, the cosmological constant, the energy of empty space predicted by quantum field theory. And the amount of vacuum energy predicted by quantum field theory is 10 to the 123 times larger than what we observe. That mismatch is not a detail. It's not a correction term you can add later. It's a fundamental failure. The theory that's supposed to predict the cosmological constant gets it wrong by more than 100 orders of magnitude. And yet, the cosmological constant is there. It's real. It's measured. It's running the universe. This is the paradox. Dark energy works as an explanation. It fits the data. It matches the observations. It predicts the right expansion rate, the right evolution of structure, the right distribution of galaxies across cosmic time. The cosmological constant is one of the most successful ideas in cosmology. And it's also one of the most disastrous predictions in the history of physics. Success and failure sitting side by side, both undeniable, both pointing to the same underlying phenomenon. Vacuum energy is real, vacuum energy is wrong. Both statements are true, and the gap between them is not closing. Physicists have been living with this paradox for decades. When the supernova results came out in 1998, some hoped it was a mistake. Maybe the supernovae were dimmed by dust. Maybe the data was contaminated. Maybe there was a systematic error nobody had caught. But the measurements held up. Other teams confirmed the results. Other methods, the cosmic microwave background, baryon acoustic oscillations, gravitational lensing, all pointed to the same conclusion. The universe is accelerating. Dark energy is real. The vacuum has energy. And the amount of energy it has is absurdly, impossibly smaller than what the equations predict. This is not a problem you can hand-wave away. It's not a loose end, it's a crisis. The two pillars of modern physics, quantum field theory and general relativity, are giving contradictory answers to one of the most basic questions you can ask. What is the energy of empty space? Quantum field theory says it's enormous. General relativity says if it were that enormous, the universe wouldn't exist. Observations say it's tiny, but non-zero. All three statements are correct within their own frameworks, and they don't fit together. Something is missing, something big, something that changes the picture in a way we haven't figured out yet. The vacuum catastrophe is not just an academic puzzle, it's a signpost. A flashing neon sign saying the map is incomplete. We're navigating with two different maps, both tested, both trusted, and they disagree about the territory by more than 100 orders of magnitude. You can't ignore a disagreement that large. You can't patch it with a small correction. You need a new map, or a new way of reading the old maps, or a deeper understanding of what the maps are actually showing. Until someone finds that understanding, the vacuum catastrophe will sit at the center of cosmology, unresolved, unanswered, and getting more uncomfortable every year. The universe is expanding, dark energy is pushing it, the vacuum is in control. And we have no idea why the vacuum has the energy it does, instead of tearing itself apart the moment it began. The problem is staring at you, more than 100 orders of magnitude, a discrepancy so large it makes every other failed prediction in the history of science look like a rounding error. The vacuum energy density predicted by quantum field theory should tear the universe apart. The vacuum energy density we actually observe is holding the universe together and gently accelerating its expansion. Both statements come from solid physics. Both are backed by mountains of evidence, and they contradict each other so completely that something fundamental has to give. So what do you do when your two best theories tell you the universe shouldn't exist? You start proposing solutions, wild solutions, desperate solutions, solutions that sound like science fiction until you realize they're the only options left on the table. And for the last few decades, that's exactly what physicists have been doing, throwing ideas at the vacuum catastrophe, one after another, hoping something sticks. None of them have stuck yet. But the attempts themselves tell you how serious the problem is. When the best minds in physics start talking about extra dimensions and parallel universes and the anthropic principle not as speculation but as legitimate lines of attack, you know the foundation is cracked. The most popular idea for decades was supersymmetry. The reasoning was elegant, almost too elegant. In quantum field theory, every particle contributes to the vacuum energy. Fermions, particles like electrons and quarks that have half-integer spin, contribute negative vacuum energy. Bosons, particles like photons and gluons that have integer spin, contribute positive vacuum energy. The signs are opposite. So if you could arrange things so that every fermion had a corresponding boson partner with the same mass, the contributions would cancel exactly, positive and negative adding to zero. The vacuum energy density would be zero. Problem solved. Supersymmetry does exactly that. It's a hypothetical symmetry that pairs every particle in the standard model with a superpartner. Every fermion gets a boson partner. Every boson gets a fermion partner. Electrons have selectrons. Quarks have squarks. Photons have photinos. The naming convention is terrible, but the math is beautiful. In a perfectly supersymmetric universe, the vacuum energy contributions from particles and their superpartners cancel completely. The cosmological constant is zero, not tiny, zero, exactly zero. That would solve the vacuum catastrophe in one stroke. The trouble is, the universe is not perfectly supersymmetric. If it were, we'd have seen the superpartners by now. Every time you detected an electron, you'd have an equal chance of detecting a selectron. Every photon would come with a photino. The Large Hadron Collider has been searching for superpartners since it turned on. Thousands of physicists, billions of dollars, years of data collection, nothing. No selectrons, no squarks, no photinos. If supersymmetry exists at all, it's broken. The symmetry might hold at extremely high energies, maybe near the Planck scale, but at the energies we can access, it's gone. The superpartners are either much heavier than their standard model counterparts, or they don't exist. And if supersymmetry is broken, the cancellation is incomplete. The vacuum energy density is no longer zero, it's something. The question is how much. If the symmetry breaks at a high energy scale, the residual vacuum energy could still be enormous. Supersymmetry breaking at the Planck scale would leave a vacuum energy density of order 10 to the 113 joules per cubic meter. That's still 120 orders of magnitude too large. You've made no progress. If the symmetry breaks at a lower scale, closer to the energies the LHC can probe, the vacuum energy drops, but it's still way too big. Off by dozens or hundreds of orders of magnitude. Better than 120 maybe, but nowhere near the observed value. Supersymmetry, even if it exists, doesn't solve the problem by itself. It reduces the size of the disaster, but it doesn't fix it. Some physicists have tried to salvage the idea by proposing mechanisms that make the cancellation more complete, even with broken supersymmetry. Maybe there's a fine-tuning. Maybe the breaking happens in just the right way, that the leftover vacuum energy is tiny. But fine-tuning is not an explanation. Fine-tuning is admitting you don't have an explanation and hoping the universe did the tuning for you. If you need to adjust parameters to 1 part in 10 to the 120 to make the theory match observations, you're not solving a problem. You're describing the problem in more elaborate language. Then there are extra dimensions. String theory, one of the leading candidates for a theory of quantum gravity, predicts that space has more than 3 dimensions. Not just the 3 we experience every day, up, down, left, right, forward, back, but additional dimensions curled up so small we never notice them. 6 extra dimensions in most versions of the theory, making a total of 9 spatial dimensions plus time. These extra dimensions change the game because vacuum energy in higher dimensional space can behave differently than vacuum energy in 3-dimensional space. One idea is that the vacuum energy leaks into the extra dimensions. The huge positive contribution from quantum field theory gets diluted or sequestered somehow, spread out across dimensions we can't see, leaving only a tiny residual in the 3 dimensions we inhabit. It's a clever trick. But making it work mathematically is hard. You have to specify the geometry of the extra dimensions very carefully. You have to explain why the dilution happens in just the right way to reduce the vacuum energy by exactly 120 orders of magnitude and not 119 or 121. You end up fine-tuning again. Different mechanism, same problem. Another approach involving extra dimensions is the idea that gravity itself is weaker in our three-dimensional slice of space because it spreads into the higher dimensions while other forces don't. That changes how vacuum energy gravitates. Maybe the large vacuum energy predicted by quantum field theory is real, but most of its gravitational effect leaks away into the bulk, the higher dimensional space outside our three-dimensional universe. What we observe in our slice is only a tiny fraction of the total. That's speculative. Nobody has built a version of this idea that works without introducing new problems or requiring fine-tuning elsewhere. And even if it worked, it wouldn't explain why the fraction we observe happens to be exactly the value needed to make the universe look the way it does. String theory also predicts a vast landscape of possible vacuum states. Depending on how the extra dimensions are curled up, depending on which fields are turned on and how they're configured, you get different effective laws of physics in the three-dimensional universe, different particle masses, different force strengths, different vacuum energy densities. The number of possible configurations is enormous. Some estimates put it at 10 to the 500 or more. That's a 1 followed by 500 zeros. Each configuration corresponds to a different universe with different properties, and somewhere in that landscape there should be configurations where the vacuum energy is small, not because of any deep principle, just because with that many possibilities, some of them will randomly have small vacuum energy. We observe a small vacuum energy because we happen to live in one of the rare pockets of the landscape where it's small. This is where the anthropic principle enters. The anthropic principle says that the universe we observe is not a random draw from all possible universes. It's selected. We can only observe a universe that allows observers to exist. If the vacuum energy were much larger, the universe would have expanded so fast that galaxies never formed, stars never ignited, planets never coalesced, life never appeared. There would be no one to measure the vacuum energy. If the vacuum energy were large and negative, the universe would have collapsed before anything interesting happened. Same result, no observers. The only universes where observers can exist are universes where the vacuum energy is small enough, in a narrow window, to allow structure to form and persist for billions of years. We observe a small vacuum energy because we couldn't exist in a universe with any other value. That logic has a certain appeal. It turns the question on its head. Instead of asking, why is the vacuum energy this value, you ask, why wouldn't it be? If there are countless universes with different vacuum energies, and only a tiny fraction of them support life, then of course we find ourselves in one of the tiny fraction. It's not a coincidence. It's a selection effect. You're not surprised to find yourself on a planet with liquid water and breathable air, even though most planets don't have those things. You're on this planet because you couldn't survive anywhere else. Same reasoning, bigger scale. The problem with the anthropic principle is that it's not a prediction. It doesn't tell you what the vacuum energy should be. It tells you what range it could be in and still allow observers. That range is not infinitely tight. The vacuum energy could be 10 times larger or 10 times smaller than the observed value, and structure would still form. Life might look different. Galaxies might be sparser or denser, but observers could still exist. So the anthropic principle doesn't explain why the vacuum energy is 5 times 10 to the negative 10 joules per cubic meter instead of 5 times 10 to the negative 9 or 5 times 10 to the negative 11. It just says it has to be somewhere in the neighborhood. That's better than nothing. But it's not the kind of sharp, testable prediction that makes physicists comfortable, and it requires the multiverse. If there's only one universe, the anthropic principle doesn't work. You'd still have to explain why this universe, the only one, happens to have the vacuum energy it does. But if there are many universes, maybe infinitely many, with different vacuum energies, then the anthropic argument goes through. We're in one of the rare ones where observers can exist. The multiverse is not a fringe idea anymore. Inflation, the theory that the early universe underwent a brief period of exponential expansion, naturally produces a multiverse in most versions. Different regions of space stop inflating at different times, and each region becomes its own universe, its own bubble, with potentially different properties. String theory's landscape fits naturally into this picture. Each bubble could correspond to a different point in the landscape, a different vacuum state, a different set of physical laws. This is where physics starts to sound like philosophy or theology, a multiverse you can never observe. Universes beyond the horizon where the laws of physics might be different. Selection effects replacing predictions. Some physicists embrace it, others hate it. The debate is fierce. On one side, you have people saying the anthropic principle is a legitimate scientific explanation, a way of making sense of why the constants of nature have the values they do. On the other side, you have people saying it's giving up. If you allow yourself to explain any observation by saying we're selected to observe it, you've stopped doing science. You've stopped making predictions. You're just cataloging what you see and inventing a story to make it sound inevitable. The trouble is, the alternatives aren't much better. If you reject the anthropic principle, if you insist there has to be a unique prediction for the vacuum energy that doesn't rely on selection effects, you're stuck. No known mechanism gives you a small vacuum energy without fine-tuning. Supersymmetry doesn't do it. Extra dimensions don't do it. No symmetry, no cancellation, no principle anyone has found makes the vacuum energy come out small for a reason you can write down and test. The only option left is to say we don't know yet. There's some new physics, some deeper principle that we haven't discovered. That's honest, but it's not satisfying, and it doesn't help you build the next experiment. Another line of attack is to question whether vacuum energy gravitates the way general relativity says it should. Maybe the huge positive contribution from quantum field theory is real, but it doesn't curve space-time. Maybe there's something about the nature of vacuum energy that decouples it from gravity. This is called the idea of non-gravitating vacuum energy or emergent gravity. The basic thought is that gravity might not be fundamental. It might be an emergent phenomenon, something that arises from deeper underlying physics, the way temperature emerges from molecular motion. If gravity is emergent, then maybe the relationship between energy and space-time curvature is not as straightforward as Einstein's equations suggest. Maybe vacuum energy, which is spread uniformly everywhere, doesn't contribute to curvature the way localized energy does. There are toy models that explore this. None of them work cleanly. The problem is, general relativity has been tested extensively, and it works. Gravity does couple to all forms of energy. You can't just declare that vacuum energy is special and doesn't gravitate without breaking something else. The equivalence principle, the idea that all forms of energy gravitate the same way, is one of the core principles of general relativity. Violate that, and you're rewriting the theory. Maybe that's necessary. Maybe general relativity is an approximation that breaks down when you ask about the vacuum. But you need a replacement theory that matches all the successes of general relativity and also explains why vacuum energy doesn't gravitate. Nobody has built that theory yet. Some approaches try to make the cosmological constant dynamical. Instead of being a fixed number, a constant, maybe it's a field, something that can change over time, that evolves as the universe expands. If the field starts at a high value and rolls down towards zero over billions of years, you could explain why the vacuum energy is small today, even if it was large in the early universe. The challenge is building a field that rolls slowly enough. Most scalar fields in quantum field theory either sit at a minimum or roll quickly. Getting one to coast along at just the right speed to match the observed expansion history is hard, and you still have to explain why the field ends up near zero instead of staying large or going negative. Fine-tuning again. There's also the possibility that the vacuum catastrophe is telling us quantum field theory itself breaks down when you ask about the vacuum. Maybe the zero-point energy calculation is wrong. Maybe the infinite sum doesn't represent anything physical. Maybe the modes you're summing over don't all contribute the way the naive calculation assumes. This is a more radical move because quantum field theory works so well everywhere else. The anomalous magnetic moment of the electron, the Lamb shift, the Casimir effect, all of those are explained by summing over vacuum fluctuations. The math works. The predictions match. But maybe there's something subtle, some cutoff or regulator or physical principle that changes the sum when you're asking about the total vacuum energy density instead of the difference in vacuum energy between two configurations. Nobody knows what that principle would be. But people are looking. One concrete idea along those lines is called asymptotic safety. The thought is that as you go to higher and higher energies, quantum gravity effects smooth out the divergences. Instead of the vacuum energy growing without bound as you include shorter and shorter wavelengths, gravity itself regulates the sum. The coupling constants of the theory change with energy in such a way that the sum stays finite or small. This is an active area of research. Some calculations suggest it might work. Others suggest it doesn't help with the cosmological constant problem. The jury is still out. Then there's the brute force approach. Maybe there is no explanation. Maybe the vacuum energy is just a parameter, like the mass of the electron or the strength of the electromagnetic force, and you have to measure it. You can't predict it from first principles. You just plug in the observed value and move on. That's deeply unsatisfying. The masses of particles and the strengths of forces are parameters we'd love to predict from a deeper theory, but we haven't yet. The cosmological constant feels different because the mismatch between prediction and observation is so extreme. It's not like we calculated the electron mass and got it wrong by a factor of 2. We calculated the vacuum energy and got it wrong by 10 to the 123. That's not a free parameter, that's a disaster. Some physicists argue the disaster is a clue. The fact that the prediction is so bad means we're asking the wrong question or using the wrong framework. The vacuum energy problem is not a problem to be solved within quantum field theory and general relativity. It's a signpost pointing to new physics. Maybe quantum gravity, whatever that turns out to be, has a built-in mechanism that sets the cosmological constant. Maybe in the full theory, the vacuum energy is automatically zero or automatically small for a reason we can't see yet because we don't have the full theory. That's hopeful, but it's also vague. It's saying the answer will come when we understand quantum gravity. Fine, but we don't understand quantum gravity, and we might not for decades or longer. There's also the nuclear option. Maybe the observations are wrong. Maybe dark energy isn't vacuum energy at all. Maybe it's something else, A field, a fluid, some other form of energy that just happens to look like a cosmological constant but isn't. That would mean the vacuum catastrophe is still there, still unsolved, but it's decoupled from cosmology. The vacuum energy is enormous as predicted, but it's cancelled by something we don't understand, and the dark energy we observe is a separate phenomenon. This doesn't solve the problem. It splits it into two problems. Why does the vacuum energy cancel so precisely? And what is dark energy if it's not vacuum energy? You've traded one mystery for two. The situation is frustrating. Every proposed solution either doesn't work, or works only if you fine-tune it, or requires unobservable extra structure like a multiverse, or replaces one problem with another. The vacuum catastrophe has been sitting unsolved for decades. The supernova observations confirming accelerated expansion came out in 1998. That's more than 25 years ago. In that time, thousands of papers have been written proposing solutions, conferences have been held, careers have been built around trying to crack the problem, and the scoreboard hasn't moved. The discrepancy is still 10 to the 123. The prediction is still catastrophically wrong. The observations are still solid, and no one has found a way to bridge the gap that doesn't require leaps of faith or structures we can't test. That doesn't mean physicists have given up. It means the problem is hard, genuinely hard. Not hard in the sense of needing more computing power or better data. Hard in the sense of requiring a conceptual breakthrough. A new way of thinking about what vacuum energy is, or what energy is, or what space-time is. The kind of breakthrough that happens maybe once or twice a century if you're lucky. Einstein's general relativity was that kind of breakthrough. Quantum mechanics was that kind of breakthrough. The vacuum catastrophe might be demanding another one, and we're waiting for someone to have the right idea. In the meantime, the universe keeps expanding, dark energy keeps pushing, the vacuum, whatever it is, keeps doing what it's been doing for billions of years, and physicists keep building models, running calculations, proposing mechanisms, hoping one of them will stick. Supersymmetry, extra dimensions, the anthropic principle, multiverse landscapes, non-gravitating vacuum energy, dynamical fields, emergent gravity, asymptotic safety. Every idea gets its moment. Every idea gets tested against the data, against the math, against the framework of everything else we know. And so far, every idea has come up short. The vacuum catastrophe is not going away. It's not fading into the background as a minor puzzle. If anything, it's getting more urgent. Because the more we learn about the universe, the more precise our measurements become, the clearer it is that dark energy is real and important and currently running the show. The vacuum is not passive, it's not inert, it's the dominant component of the cosmos. And we have no idea why it has the energy it does, instead of tearing space apart. That ignorance is uncomfortable. It's a crack in the foundation of physics. A reminder that for all the progress we've made, for all the precision and power of our theories, we're still missing something fundamental. Something that sits at the intersection of quantum mechanics and gravity, the two pillars holding up modern physics, and neither pillar can handle the weight. One of them has to give, or both of them do, or something new has to be built underneath to support them. We don't know which, we don't know when, we're waiting for the answer, and the universe is not offering hints. But here's the thing, the vacuum catastrophe, for all its frustration, has done something useful. It's forced physicists to think harder about what energy actually is, not what energy does. What energy is, at the level of fields and space-time and quantum fluctuations. Energy is supposed to be the thing that's conserved, the thing that takes many forms, the property that systems have. But when you ask how much energy the vacuum has, and your best theories give you an answer that's off by more than 100 orders of magnitude, you start to wonder if the question even makes sense. Maybe energy is not the kind of thing that has a total. Maybe it's not the kind of property you can assign to the universe as a whole. Maybe the vacuum energy problem is telling us that energy, at its core, is stranger and more subtle than we've been treating it. Not a substance, not a fluid, not even a number you can pin down and measure. Something else, something we haven't found the right words for yet. We've been chasing energy for 300 years, measuring it, calculating it, converting it from one form to another, tracking it through chemical reactions and electric circuits and the cores of stars, building entire industries around capturing it, storing it, moving it from place to place. And somewhere along the way, we convinced ourselves we knew what it was. Energy is the stuff that makes things happen, the fuel that powers the universe, the currency of change, except it's not stuff, it's never been stuff. And the vacuum catastrophe, that 120 orders of magnitude disaster sitting at the foundation of cosmology, is the universe's way of telling us we've been asking the wrong question all along. Energy is a property, not a thing, not a substance. Not a fluid you can bottle, or a field you can touch, or a particle you can isolate. It's a number, a value that systems have, a bookkeeping tool that nature uses to keep its accounts balanced. When you burn a log, you're not releasing energy that was stored inside the wood, like water in a bottle. You're rearranging atoms, breaking chemical bonds, allowing electrons to drop into lower energy states, and the difference in energy between the initial configuration and the final configuration shows up as heat and light. The energy was never sitting there waiting to escape. It's a property of the configuration, before and after. The number changed, that's all. This is not the story we tell ourselves. The language we use makes energy sound like a substance. Batteries store energy. Power plants generate energy. Your body burns energy when you move. All of that language is shorthand, convenient metaphors that work well enough for engineering and everyday life, but fall apart when you push them. You can't generate energy. The first law of thermodynamics won't let you. Energy is conserved. It changes forms, but the total stays constant. What power plants actually do is convert energy from one form, chemical potential in coal, kinetic energy in falling water, nuclear binding energy in uranium, into another form, electrical energy moving through wires. The total doesn't change. Only the distribution changes. And distribution is not a property of the energy itself, it's a property of the system. The confusion runs deep because we experience energy as if it were real. A hot cup of coffee feels different than a cold one. A moving car has momentum, force, the ability to crush things. A charged battery can power a light bulb. Those effects are undeniably real. But the thing causing the effects is not a substance called energy. It's the configuration of matter and fields. The temperature of the coffee is the average kinetic energy of the water molecules jittering around inside the cup. The momentum of the car is a property of its motion relative to the ground. The charge in the battery is a difference in electric potential between two terminals. All of those are relationships, configurations, states of systems. The energy is what you calculate when you want to know how much those configurations can change before they run out of room to move. Physics textbooks will tell you energy is the capacity to do work, and work is the transfer of energy. That's circular. It's defining one term with another term that's defined by the first. It's operationally useful because it tells you how to set up calculations, but it doesn't give you a picture of what energy is. And the reason it doesn't is because there's no picture to give. Energy is not an object, it's a property that objects have. Asking what energy is made of is like asking what temperature is made of, or what velocity is made of. The question doesn't pass. Temperature is a measure of molecular motion. Velocity is a measure of how fast position changes. Energy is a measure of how much a system's state can affect other systems. That's closer to the truth. Still not perfect, but closer. Einstein made it worse, or better, depending on how you look at it. E equals mc squared collapsed the distinction between matter and energy. Mass is a form of energy. Energy can take the form of mass. The universe is not made of two different kinds of stuff, matter and energy. It's made of one kind of thing, fields, and those fields have properties like energy and momentum and charge that describe how the fields behave and interact. Particles are ripples in the fields, stable localized excitations. A photon is a ripple in the electromagnetic field. An electron is a ripple in the electron field. The ripples have energy. They also have momentum. They also have other properties, spin, charge, things you can measure and calculate. But none of those properties are substances. They're aspects of the ripple. Ways of describing how the field is behaving at that point in space and time. When you take that picture seriously, asking what the energy of the vacuum is becomes a very strange question. The vacuum is the state where all the fields exist, but nothing is rippling through them. No particles, no disturbances, just the fields in their lowest energy configuration. But quantum mechanics says the lowest energy configuration is not zero energy. The uncertainty principle won't allow it. Every field, every mode, every possible wavelength contributes a bit of zero-point energy. The vacuum hums, it fluctuates. Virtual particles flicker in and out of existence. And all of that activity, all of those fluctuations, should contribute to the total energy density of empty space. Add them up, and you get a number, a very large number. 10 to the 113th joules per cubic meter if you cut the sum off at the Planck scale. That's the vacuum energy density according to quantum field theory. But the vacuum energy density we actually observe is 10 to the negative 10th joules per cubic meter. The prediction is 10 to the 123 times too large. That's not a rounding error. That's not a missed correction term. That's a complete and total failure of the theory to predict something as basic as the energy of the background. And the failure is so extreme, so far beyond anything else in the history of physics, that it forces you to ask whether the question even makes sense. Maybe asking for the total energy of the vacuum is like asking what the universe's position is. Position relative to what? The universe is everything. There's no external reference frame. Maybe energy, when you try to apply it to the whole of space, to the vacuum itself, runs into a similar problem. Energy of the vacuum compared to what? Energy is always a difference, a change, a comparison between two configurations. Maybe trying to assign an absolute energy to the vacuum is asking the wrong kind of question. Except the universe won't let you off that easy. Because the vacuum energy, whatever it is, gravitates. General relativity says energy curves space-time, all energy, including the energy of empty space, and the curvature of space-time determines how the universe expands, whether it speeds up or slows down, whether space is flat or curved. All of that depends on the energy density filling space. You can't just say the vacuum energy is a meaningless number because it's not. It shows up in the expansion rate of the universe. It's measured, it's real. Dark energy is real. The cosmological constant is real. And its value, 5 times 10 to the negative 10th joules per cubic meter, is one of the most precisely measured numbers in all of cosmology. So the vacuum has energy, That energy gravitates, and the amount of energy it has is catastrophically, absurdly smaller than what quantum field theory predicts. That mismatch is telling us something. Not just that our calculations are wrong, that our framework is incomplete. Quantum field theory works. It predicts the anomalous magnetic moment of the electron to 12 decimal places. It explains the Casimir effect, the Lamb shift, every scattering experiment ever performed. General relativity works. It predicts the orbit of Mercury, the bending of light, the existence of black holes and gravitational waves. Both theories have been tested more rigorously than any other theories in the history of science. And when you ask them to work together, when you ask what the energy of the vacuum is and how that energy curves space-time, they give you an answer that's wrong by more than 100 orders of magnitude. That's not a bug in the calculation, that's a signpost. A flashing neon sign saying something fundamental is missing. The vacuum catastrophe is not a problem to be solved within the current framework. It's evidence that the framework itself is incomplete. Quantum field theory is not the final word on what fields are or how they behave. General relativity is not the final word on what space-time is or how gravity works. There's a deeper theory underneath. A theory that includes both quantum mechanics and gravity, that explains how space-time emerges from something more fundamental, that makes sense of what energy actually is at the deepest level. Physicists call it quantum gravity. Nobody has it yet. Nobody knows what it looks like. But the vacuum catastrophe is one of the clearest pieces of evidence that it's needed. String theory tries. Loop quantum gravity tries. Other approaches, asymptotic safety, causal set theory, emergent spacetime, all of them are attempts to build a framework where quantum mechanics and gravity fit together without contradictions. Some of them suggest the vacuum energy problem resolves naturally in the full theory. Others suggest the cosmological constant is a parameter you have to measure, not something you can predict. None of them have succeeded yet. None of them have made a prediction you can test that distinguishes them from the others. The quest for quantum gravity is ongoing. It's been ongoing for decades, and the vacuum catastrophe sits there, unsolved, waiting for someone to have the right idea. In the meantime, we're left with a puzzle. Energy is conserved. That's a law. One of the most tested, most reliable laws in all of physics. The total energy in an isolated system does not change. It can shift around. Kinetic to potential, chemical to thermal, mass to radiation, but the sum stays constant, except when it doesn't. In an expanding universe, energy conservation is more subtle. The universe is not an isolated system. Space itself is changing, and when space changes, the total energy can change too. Dark energy, the vacuum energy driving the accelerated expansion, has a constant density. As space expands, the volume increases, and so does the total amount of dark energy. More space means more vacuum energy. The total is growing. That sounds like a violation of energy conservation. It's not, exactly, because general relativity allows it. Energy conservation in general relativity is local, not global. Locally, in any small region of space, energy is conserved. Globally, across the whole universe, the total energy can change if space-time itself is dynamic, but it's uncomfortable. It pushes the concept of energy to its limits. And it raises the question whether energy, as we've defined it, is the right concept to be using. Maybe energy is an emergent property, something that makes sense in certain regimes, certain limits, but breaks down when you ask about the whole universe or the deepest level of reality. Temperature is an emergent property. It's a useful concept when you're talking about a system with many particles, but it doesn't make sense for a single atom. You can't ask what the temperature of one molecule is. The question is meaningless. Maybe energy is similar. Maybe it's a concept that works beautifully in the classical limit, in the regime where quantum mechanics and gravity don't overlap, but stops being well defined when you push into the extreme corners of physics. The vacuum catastrophe might be telling us we've reached the edge of where the concept applies. That's unsettling. Energy is supposed to be fundamental. It's the thing that's conserved. The quantity that underlies everything from mechanics to thermodynamics to relativity to quantum field theory. If energy itself is not fundamental, if it's emergent or approximate or context-dependent, then what is fundamental? Fields, space-time geometry, information, some deeper structure we haven't named yet? Nobody knows. And the vacuum catastrophe is not giving easy answers, it's giving hard questions. There's a philosophical dimension here that's worth pausing on. The vacuum catastrophe is not just a technical problem, it's a confrontation with the limits of human understanding. We've built two of the most successful theories ever conceived, quantum field theory and general relativity. Together, they explain almost everything we've ever observed: the behavior of subatomic particles, the dynamics of galaxies, the expansion of the universe, the formation of black holes, the bending of light, the decay of isotopes. All of it fits into one framework or the other. And yet there's this one question: what's the energy of empty space? And the two theories give answers that differ by more than 100 orders of magnitude. That's not a small gap, that's a chasm. And it suggests that despite all our progress, despite all the precision and power of modern physics, we're still missing something central. The missing piece might be small, a symmetry we haven't noticed, a field we haven't discovered, a term in the equations we overlooked, or it might be large. A complete rethinking of what space-time is, what quantum states are, what it means for something to exist. The vacuum catastrophe doesn't tell you which. It just tells you the current picture is wrong, incomplete. And the incompleteness is not hiding in some obscure corner of parameter space. It's sitting at the foundation, the energy of the vacuum, the baseline. The thing that should be the easiest to calculate and instead turns out to be the hardest. Some physicists find this exciting. A problem this big means there's a breakthrough waiting, a new principle, a new framework, something that will change the landscape the way general relativity changed it a century ago. Others find it frustrating. Decades of work, thousands of papers, no progress on closing the gap. The optimists say the breakthrough is coming. The pessimists say maybe the problem is unsolvable with the tools we have. Maybe it requires experimental data from energy scales we'll never reach. Maybe it requires a conceptual leap no one has figured out how to make yet. Maybe both are right. The breakthrough is coming, but not soon, and not without new data or new mathematics or new ways of thinking that haven't been invented yet. The anthropic principle offers a way out, sort of. If there's a multiverse, if there are countless universes with different vacuum energy densities, then the value we observe is explained by selection. We're in a universe where the vacuum energy is small because only in such universes can structure form and observers evolve. That doesn't tell you why the multiverse exists, or why it explores different values, or what the underlying mechanism is. It just says the value we measure is not a coincidence, it's a requirement. We couldn't exist anywhere else. That logic is either profound or defeatist, depending on who you ask. It might be the right answer. It might be giving up on finding a deeper explanation, or it might be both. A correct answer that doesn't satisfy the desire for a mechanistic, predictive theory. What's clear is that the vacuum catastrophe is not going away. It's been sitting there since the late 1960s, when cosmologists first started putting limits on the cosmological constant. It became a full crisis in 1998, when the accelerated expansion was confirmed and dark energy became unavoidable. That's more than 25 years ago. In that time, the data has gotten better. The measurements are more precise. The vacuum energy density is known to a few percent. The theoretical prediction, 10 to the 113th joules per cubic meter, hasn't changed. The observed value, 10 to the negative 10th joules per cubic meter, hasn't changed. The discrepancy is still 10 to the 123, the worst prediction in the history of science. And no proposed solution has closed the gap without invoking new structures we can't test or fine-tuning we can't justify. So where does that leave us? With a choice. You can treat the vacuum catastrophe as a technical problem, a calculation that went wrong somewhere, a symmetry that got broken in a way we don't understand yet, a parameter that needs to be measured rather than predicted. Or you can treat it as a signpost, evidence that the concepts we're using, energy, space-time, quantum fields, are approximations that work in certain regimes but break down when you push them to their limits. That the universe at its deepest level is not made of the things we think it's made of. That the framework we've built, for all its success, is still a map, not the territory, and the map has blank spaces we haven't filled in yet. Energy is one of those blank spaces. We know how to calculate it, we know how to measure it, we know it's conserved, locally if not always globally. We know it takes many forms, and those forms are interconvertible. We know mass is energy, and energy can become mass. We know quantum fields have zero-point energy, and virtual particles contribute to real effects. We know all of that. And we still don't know what energy is, not at the level of what are we actually talking about when we say a system has energy. Is it a property of the fields? A property of space-time? A bookkeeping device that happens to correspond to something real? A useful fiction that works in the classical limit but has no precise meaning in the full quantum theory? The vacuum catastrophe forces that question into the open. Because if you can't predict the energy of the vacuum, if your best calculation is off by more than 100 orders of magnitude, then maybe energy is not the kind of thing that has a single well-defined value you can calculate from first principles. Maybe it's context-dependent, maybe it's emergent, maybe it's a property that only makes sense when you're comparing two states, not when you're asking about the absolute value of a single state. The vacuum is the ground state, the lowest energy configuration, but lowest compared to what? If there's nothing to compare it to, does the question of how much energy it has even have a meaning? These are not rhetorical questions, they're live questions. Questions physicists are actively thinking about, arguing about, writing papers about. And the fact that they're still open after decades of work tells you how deep the problem goes. The vacuum catastrophe is not a puzzle you solve by finding the right equation. It's a challenge to the entire way we think about energy and space-time and quantum fields. It's asking whether the concepts themselves are adequate, whether the language we're using is the right language, whether the questions we're asking are well-formed. And maybe that's the real lesson, not that we don't know the answer, that we don't know the question. We've been asking, what is the energy of the vacuum? And the universe has been giving us an answer that doesn't make sense. 10 to the 113th from the theory, 10 to the negative 10th from observation, 120 orders of magnitude apart. Maybe the problem is not that we calculated wrong. Maybe the problem is that what is the energy of the vacuum is not a question the universe knows how to answer in the framework we're using. Maybe the question needs to be rephrased, reframed, asked in a different language, a language we haven't built yet. That's where the quest stands. not at an answer, at a better question. The vacuum catastrophe is a reminder that for all our progress, for all the power and precision of modern physics, we're still explorers, still mapping territory we don't fully understand, still stumbling into contradictions that tell us the map is incomplete. Energy is conserved. Energy is a property, not a thing. Energy is what systems have, what fields carry, what makes change possible. And energy, when you ask about the vacuum, gives you an answer so wrong it breaks the theory. All of those statements are true, and they don't fit together, not yet. The universe is under no obligation to make sense to us. It doesn't care whether our equations balance or our concepts cohere. It just is. And our job, as scientists, as thinkers, as curious creatures trying to make sense of existence, is to keep asking, keep calculating, keep testing, keep building frameworks and tearing them down when they fail. The vacuum catastrophe is a failure, a spectacular, undeniable 120 orders of magnitude failure, and failures are where progress comes from, not from getting things right, from getting things wrong in ways that force you to rethink everything you thought you knew. Energy is a property, not a thing. That's the closest we've come to the truth. It's a number that systems have, a measure of how much they can change, a bookkeeping tool that nature uses to keep the universe from violating its own rules. It's conserved because symmetries are conserved, because the laws of physics don't change over time, because the universe has structure, and that structure constrains what can happen. Energy is real in its effects. The Casimir force is real. The expansion of the universe is real. The mass of particles is real. All of those are manifestations of energy doing what energy does, but energy itself is not a substance, not a fluid, not a field you can touch. It's a property, an aspect, a way of describing the state of the world, and the vacuum catastrophe is telling us that even that description is not complete, that there's a deeper layer, a more fundamental picture, where the concepts we're using now, energy, space-time, fields, particles, resolve into something simpler or stranger or more subtle. We don't have that picture yet. We don't know what it looks like. We don't know when it will arrive. But the vacuum catastrophe is the clearest sign we have that it's out there, waiting to be found. And when someone finally finds it, when the pieces click into place and the discrepancy resolves and the vacuum energy makes sense, it won't just solve one problem, it will change everything. The way we think about energy, the way we think about space, the way we think about what exists and why. That's the prize, that's what's at stake. Not just an answer to a calculation, a new understanding of reality itself. Until then, we calculate, we measure, we argue, we propose theories and test them and discard them when they fail. We live with the discomfort of knowing our best theories are wrong by more than 100 orders of magnitude, and we don't know why. We live with the vacuum catastrophe, unsolved, unresolved, sitting at the foundation of cosmology like a crack in the bedrock. And we keep going, because the questions are too interesting to ignore, because the universe is too strange to walk away from. Because energy, whatever it is still the key to understanding how everything works. We just don't have the lock yet. We're still looking for it. Still feeling around in the dark. Still asking what energy is, really, at the deepest level, and listening to the universe give answers we don't quite understand. That's the quest. That's where we are. Not at the end, at the beginning. Still searching, still wondering. Still chasing the question we don't yet know how to ask. So here we are, 14 billion years after the universe began, sitting on a planet that took 4.5 billion years to cool, using instruments we invented in the last century to ask a question that might not have an answer. What is energy? We've been chasing it for 300 years. We've measured it, converted it, tracked it through chemical reactions and particle collisions and the cores of dying stars. We've built cities around capturing it, economies around distributing it, entire branches of physics around calculating it. And after all that work, after all that precision, we still don't know what it is. Not really. Not in the way you can point to an electron and say that's a particle, or point to a wave and say that's a disturbance in a field. Energy is slippier. It's a property, a number, a bookkeeping tool the universe uses to keep its accounts balanced. And the vacuum catastrophe, that stunning 10 to the 120 times mismatch between prediction and observation, is the universe handing us back our homework with a failing grade. Not because we calculated wrong, because we asked the wrong question, because the framework we built, for all its beauty and power, is still incomplete, still missing something fundamental. The vacuum is not empty. Quantum mechanics proved that. The vacuum has energy. General relativity demands that, and the amount of energy it has should have destroyed the universe before it began. Except it didn't. We're here. The stars are shining. Space is expanding gently, accelerating just enough to notice but not enough to tear anything apart. And the gap between what should be and what is stands as the largest unsolved problem in physics. Not a minor puzzle, a crack in the foundation. Maybe the crack is where the light gets in. Maybe the catastrophe is a gift, a sign that there's something deeper waiting to be found, a new principle, a new symmetry, a new way of thinking about what exists and why. The vacuum catastrophe is not the end of the story. It's the beginning of the next chapter. And whoever writes that chapter will change everything. Not just cosmology, not just physics. The way we understand reality itself, what energy is, what space is, what it means for something to be. Until then, the universe keeps its secrets. The vacuum keeps ticking, and we keep asking, because the question is too strange to ignore, because the discrepancy is too large to explain away, because somewhere in the gap between theory and observation, between what we predict and what we measure, is a truth we haven't seen yet, a truth about energy, about existence, about the nature of the cosmos at its most fundamental level. We don't have it yet, but it's out there, waiting.